From dark matter to exoplanets, from the Big Bang to black holes, our cosmos is filled with phenomena that challenge our understanding of physics. In this documentary, we'll examine the most intriguing mysteries of our universe, exploring current scientific theories and cutting-edge observations. Join us as we delve into the most fascinating mysteries in our universe. The observable universe refers to the part of the universe that we can see or detect from Earth, extending approximately 13.8 billion light-years in every direction. This vast expanse contains billions of galaxies, each home to millions or even billions of stars, along with countless planets. The limitation of this observable section lies in the fact that it is bounded by the speed of light. Anything farther away than this distance cannot be seen because the light from those objects has not had enough time to reach us since the beginning of the universe. What makes the observable universe so fascinating is that it is not only a stretching fabric of space, but also a rich tapestry of cosmic history. The light we receive from distant galaxies gives us a glimpse into the universe's past, revealing how these celestial bodies have evolved over billions of years. As we look deeper into space, we are essentially peering back in time, witnessing events that occurred long before humanity even existed. In contrast, the entire universe encompasses everything, including regions beyond our observational reach. These areas may contain more galaxies, stars, and planets that we cannot detect due to the light from these objects not yet reaching us, or because they are moving away from us so rapidly that their light is redshifted beyond our visibility. The true extent of the universe is still a topic of speculation and research, as we do not know if it is finite or infinite in size. Additionally, while we have a well-defined boundary for the observable universe, the entire universe may very well extend far beyond this boundary, possibly infinitely. This reality challenges our understanding of the cosmos, prompting scientists to explore theories about its curvature and structure, while also grappling with the mysteries of dark matter and dark energy that make up a significant portion of the universe's overall composition. Measuring the size of the observable universe relies on a combination of observation, light travel time, and the principles of cosmology. The foundation of this measurement begins with understanding the speed of light, which is constant in a vacuum and takes about 8 minutes to travel from the Sun to Earth. When astronomers observe distant galaxies, they are receiving light that has taken billions of years to reach us. This light effectively acts as a time capsule, allowing us to see these galaxies as they were in the past. To calculate the size of the observable universe, astronomers determine the distance to various celestial objects using different methods, such as parallax, standard candles like supernovae, and redshift measurements. Parallax involves observing a nearby star from 2 different positions in the Earth's orbit, which can yield its distance relative to our solar system. Standard candles rely on the predictable brightness of certain types of supernovae or variable stars, allowing astronomers to calculate the distance based on how dim they appear. Redshift, on the other hand, measures the change in wavelengths of light from distant galaxies as they move away from us, confirming the expansion of the universe and aiding distance estimations. Once these distances are measured, the maximum observable distance is defined, which culminates in the boundary of the observable universe. Given that the universe has been expanding since the Big Bang, the light we see from the most distant reaches has traveled for billions of years. This means that the furthest edges of the observable universe can effectively be estimated at around 13.8 billion light-years in every direction. These calculations are continuously refined with advancements in technology and improved observational methods. Instruments like the Hubble Space Telescope and future missions such as the James Webb Space Telescope will enhance our understanding of cosmic distances. As our capability to observe the universe grows, so does our grasp of its enormity, revealing not only the distances we can measure, but also inviting intrigue about the regions beyond our reach. The most distant objects we can see in the observable universe are primarily galaxies, with some of them dating back to shortly after the Big Bang. One significant example is a galaxy named GNZ11, which is located approximately 13.4 billion light-years away from Earth. Observations have revealed that this galaxy existed just about 600 million years after the creation of the universe. This remarkable distance means that when we observe GNZ11, we are looking at one of the earliest times in cosmic history, offering a glimpse into the formation of galaxies shortly after the universe began to cool and expand. Another extraordinary object is a galaxy called HD1, which has been reported to exist around 13.5 billion light-years away. This has led astronomers to believe that it might have come into existence even earlier than GNZ11, allowing researchers to study conditions prevalent during the universe's infancy. The light we observe from these galaxies provides key insights into the processes of star formation and the evolution of cosmic structures in the early universe. In addition to these galaxies, scientists also identify extremely distant quasars. Quasars are highly luminous active galactic nuclei powered by supermassive black holes at the centers of galaxies. One of the most distant known quasars, designated J001, is located around 13 billion light-years away as well. It formed just 700 million years after the Big Bang, showcasing how active galactic nascent formations occurred even in the universe's early stages. These distant objects challenge our understanding of cosmic evolution, as they reveal conditions that existed in a time when the universe was still young and chaotic. They entice astronomers to delve deeper into questions about galaxy formation and the fundamental laws governing cosmic dynamics. Each discovery nudges us closer to unraveling the mysteries of our universe, prompting ongoing research to observe even more distant celestial bodies and to better understand the timeline of its development. Our understanding of the observable universe has undergone a profound transformation since humanity first gazed at the night sky. In ancient times, celestial bodies were often viewed through the lens of mythology and religion, with civilizations attributing patterns to constellations without understanding their true nature. The Renaissance marked a significant turning point when astronomers like Copernicus and Galileo challenged the geocentric model, revealing that the Earth is not the center of the universe but rather orbits the Sun in a vast expanse filled with countless stars. As telescopes evolved, so did our comprehension of the universe's structure and scale. The advent of the 18th and 19th centuries brought figureheads such as Edwin Hubble, whose observations revealed that many nebulae were actually separate galaxies, dramatically expanding our understanding of the cosmos. Hubble's discoveries led to the realization that not only was our galaxy one among many, but galaxies were moving away from us, supporting the idea of an expanding universe. This observation laid the groundwork for the Big Bang theory, fundamentally reshaping our understanding of cosmic origins and the development of the universe. In more recent decades, the discovery of cosmic microwave background radiation provided compelling evidence for the Big Bang model, allowing scientists to probe the universe's early moments. Technological advancements, including space telescopes and improved detection methods, have further enhanced our ability to observe distant galaxies, leading to breakthroughs in measuring the universe's expansion rate and understanding dark matter and dark energy. These components make up a substantial part of the universe's structure, yet their nature remains one of the biggest mysteries in modern cosmology. As our observational capabilities improve, so too does our appreciation for the universe's complexity. New missions, such as the James Webb Space Telescope, aim to push the boundaries of our understanding even further by examining the early formation of galaxies, stars, and planetary systems. The more we explore the observable universe, the more questions arise, inviting both scientists and enthusiasts alike to ponder the cosmos's vastness, its intriguing mysteries, and our place within it. The cosmic microwave background radiation, often referred to as the CMB, plays a crucial role in our understanding of the observable universe. This faint afterglow of the Big Bang is a key piece of evidence that supports the Big Bang theory, which describes the origin and evolution of the universe. Discovered in the mid-20th century, the CMB represents the remnants of thermal radiation from a time when the universe was young, hot, and dense, approximately 390,000 years after the Big Bang. The CMB is uniformly spread across the sky and can be detected in every direction, providing a snapshot of the universe during a significant phase known as recombination. At this time, protons and electrons combine to form neutral hydrogen atoms, allowing photons or light particles to travel freely. Before recombination, the universe was opaque, filled with free electrons that scattered light. The release of the CMB marks the moment when the universe became transparent, allowing the light to travel through space as we observe it today. By analyzing the slight temperature fluctuations and anisotropies in the CMB, scientists can infer valuable information about the universe's structure, composition, and evolution. These fluctuations indicate variations in density that ultimately led to the formation of galaxies and clusters throughout time. The data from the CMB also helps determine key cosmological parameters, including the ages of the universe and the ratios of its contents, such as normal, dark, and dark energy. Furthermore, the CMB provides a baseline for understanding the large-scale properties of the universe. Measurements from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have allowed scientists to refine their models of cosmic evolution, enhancing our grasp of fundamental questions regarding the universe's geometry and its expansion rate. As a fundamental cornerstone of modern cosmology, the cosmic microwave background continues to be a significant focus of research, opening new pathways to explore the mysteries of our universe and its origins. Several lines of evidence robustly support the Big Bang theory, which outlines the origin and evolution of the universe. One of the most significant pieces of evidence is the cosmic microwave background radiation, or CMB. This remnant radiation from the early universe is uniform across the background of the sky and serves as a snapshot from approximately 390,000 years after the Big Bang. The CMB's existence aligns perfectly with the predictions of the Big Bang model and demonstrates that the universe expanded from a hot, dense state, now cooling to the point where this radiation can be detected. Another key piece of evidence comes from the observed redshift of distant galaxies. Edwin Hubble's discovery that galaxies are moving away from us, and the farther they are, the faster they seem to be receding, supports the idea that the universe is expanding. This phenomenon, known as Hubble's law, implies that the universe was once confined to a much smaller point, which aligns with the theoretical foundation of the Big Bang. If the universe is expanding today, it suggests that it had to originate from a hot, compressed state. Additionally, the abundance of light elements provides strong corroboration for the Big Bang theory. The theory predicts that the universe's early moments resulted in the formation of helium, deuterium, and other light elements through a process known as Big Bang nucleosynthesis. Observations of the current abundances of these elements in the universe closely match the predictions, reinforcing the idea that they were formed in the hot, dense conditions that characterized the early universe. Moreover, the large-scale structure of the universe also offers support for the Big Bang theory. The distribution of galaxies and galaxy clusters across cosmic distances displays patterns that can be explained by the growth of density fluctuations from the early universe as it cooled and expanded. Computer simulations based on the Big Bang framework successfully recreate these structures, further solidifying the model's validity. Together, this evidence paints a coherent picture of cosmic evolution, making the Big Bang theory the prevailing explanation for the origins of the universe. During the first few seconds after the Big Bang, the universe underwent rapid and extreme changes in temperature, density, and energy. This period, often referred to as the Planck epoch, lasted for approximately 10 to the negative 43 seconds. The universe was unimaginably hot, with temperatures exceeding temperatures that will never be encountered again, and it was filled with a dense mix of elementary particles like quarks, electrons, and neutrinos, all existing in a state of chaos and equilibrium. As the universe expanded, it cooled significantly. In the subsequent moments, specifically during the first 100 seconds, quarks began to combine to form protons and neutrons in a process called baryogenesis. These protons and neutrons then entered a phase of rapid formation known as nucleosynthesis, where they combined to form heavier atomic nuclei. Helium emerged as the primary product, along with trace amounts of other light elements like deuterium and lithium. This synthesis process laid the groundwork for the elemental composition of the universe. Helium emerged as the primary product, along with trace amounts of other light elements like deuterium and lithium. This synthesis process laid the groundwork for the elemental composition of the universe. By around 390,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms, marking the moment referred to as recombination. This transition transformed the universe from an opaque plasma into a transparent space, allowing photons to travel freely. The release of these photons is what we now observe as the cosmic microwave background radiation. The dynamics of this early universe were governed by fundamental forces. As it expanded, gravity began to exert its influence, leading to the formation of the large-scale structures we observe today. The seeds of galaxies were planted in the density fluctuations present in the early universe, eventually leading to the rich complexity of cosmic structures that continued to develop over billions of years. This initial period after the Big Bang laid the foundation for everything that followed, establishing the very laws of physics and the fundamental particles that constitute matter in the universe. Cosmic inflation refers to a brief, exponential expansion of the universe that is believed to have occurred within the first tiny fraction of a second after the Big Bang, specifically between 10 to the negative 32nd and 10 to the negative 35th seconds. During this period, the universe expanded at a staggering rate, increasing in size by a factor of at least 100 trillion times. This incredibly rapid growth helps explain several critical features of the universe we observe today. One of the most compelling implications of cosmic inflation is its ability to account for the observed uniformity of the universe, often referred to as isotropy. When astronomers look in any direction in the sky, they find the cosmic microwave background radiation consistent in temperature, with only minor fluctuations. Without inflation, it would be difficult to explain why regions of the universe that are so far apart, and thus seemingly unconnected, exhibit such uniform characteristics. Inflation proposes that those parts of the universe were once in close proximity before the rapid expansion stretched them apart, smoothing out any initial irregularities and leading to the uniformity we observe. Inflation also offers an explanation for the large-scale structure of the universe. The rapid expansion amplified quantum fluctuations that existed at the subatomic level during the early moments after the Big Bang. As the universe expanded, these fluctuations were stretched to cosmic scales, serving as the initial seeds for the formation of galaxies and other structures. Therefore, cosmic inflation not only reconciles the uniformity of the universe, but also provides a framework for understanding the density variations that ultimately led to complex cosmic formations. Further, inflation predicts that the universe is not only flat, but also that it has a large-scale structure influenced by the distribution of matter and energy. Observational evidence, including measurements of the cosmic microwave background and large-scale galaxy surveys, supports the idea that the universe has the geometric properties consistent with inflation. As our understanding of inflation evolves, it continues to offer intriguing insights into the very nature of the universe and the mechanisms governing its expansion and structure. The formation of the first elements in the early universe occurred through a process known as Big Bang nucleosynthesis. This process took place within the first few minutes after the Big Bang, when the universe was hot and dense enough to allow nuclear reactions to occur. Initially, the universe was filled with a high-energy plasma composed primarily of protons, neutrons, and electrons. As it expanded and cooled, conditions became favorable for these subatomic particles to combine and form simple atomic nuclei. During the first moments after the Big Bang, protons and neutrons formed from quarks, which are the fundamental particles that make up protons and neutrons. Shortly thereafter, these protons and neutrons began to combine through nuclear fusion. Within the first few minutes, a significant portion of protons fused to create helium nuclei, specifically helium-4, which consists of 2 protons and 2 neutrons. In addition to helium, trace amounts of other light elements, such as deuterium, lithium, and beryllium, were also synthesized during this period due to various fusion reactions. The equilibrium found during this phase of nucleosynthesis was highly sensitive to the temperature and density of the universe. As the universe continued to expand and cool, it quickly became too cold for nuclear reactions to proceed, which effectively halted the formation of new nuclei. By about 5 minutes after the Big Bang, the universe had cooled enough that approximately 25% of its mass consisted of helium, while the remaining 75% was primarily hydrogen, with only minor amounts of deuterium and lithium. The primordial elements formed during this critical period laid the foundation for the subsequent formation of stars and galaxies. Over the billions of years that followed, stars ignited, fusing hydrogen and helium into heavier elements through stellar nucleosynthesis. Consequently, the matter in our universe evolved into the rich array of elements we observe today, ultimately contributing to the makeup of planets and the building blocks of life. The study of Big Bang nucleosynthesis remains vital for understanding the origins of these first elements and their significance in the cosmic timeline. The cosmic web is the large-scale structure of the universe that resembles a vast network of interconnected filaments and bubbles formed by galaxies, galaxy clusters, and dark matter. It is a remarkable display of cosmic architecture, where galaxies are not randomly distributed but align along intricate patterns. The cosmic web consists of dense regions known as knots or clusters, separated by vast voids where very few galaxies exist. The formation of the cosmic web began in the early universe with quantum fluctuations that occurred during the inflationary period shortly after the Big Bang. These tiny density variations in the primordial plasma acted as seeds for the large-scale structures that would develop over billions of years. As the universe expanded and cooled, matter began to clump together under the influence of gravity. Regions that were slightly denser than their surroundings attracted more matter, leading to the formation of the first stars and galaxies. Over time, as gravitational forces continued to pull matter together, these early structures merged and grew, forming larger and more complex configurations. The gravitational interplay between the visible matter and the unseen dark matter facilitated the growth of large structures. Dark matter, which does not interact with electromagnetic forces, accounts for a significant portion of the universe's mass and plays a crucial role in shaping the cosmic web. It influences how ordinary matter gravitates and organizes into filaments and knots in the universe. As galaxies formed and evolved, they accumulated gas and dust, creating environments conducive to star formation. Galaxy clusters emerged from the merging of smaller groups, and their gravitational attraction further influenced the surrounding structures. The intricate network that characterizes the cosmic web is a testament to the dynamic processes of cosmic evolution. Current observational techniques, including large galaxy surveys and simulations, are continually refining our understanding of the cosmic web, revealing its complexity and the underlying physics that govern the growth and distribution of galaxies in the universe. The proposal of dark matter emerged from several pivotal observations in astrophysics that revealed inconsistencies between the visible matter in galaxies and the gravitational effects observed in these systems. One of the earliest indications came from the studies of galaxy rotation curves. Astronomers expected that the speed at which stars orbit the center of a galaxy would decrease with distance, similar to how planets behave in our solar system. However, observations showed that stars at the edges of galaxies were moving at high speeds, suggesting that there was much more mass present than could be accounted for by the visible stars and gas. This discrepancy indicated the existence of unseen mass, often referred to as dark matter, exerting gravitational influence on the stars. Another significant line of evidence came from the study of galaxy clusters. Observations revealed that the mass of galaxy clusters, determined through various methods, such as the motions of individual galaxies within them, was much greater than the mass that could be accounted for by the visible matter alone. The gravitational binding of clusters indicated the presence of a substantial amount of non-luminous matter, which further supported the dark matter hypothesis. The existence of dark matter was further solidified through observations of the gravitational lensing effect, where light from distant galaxies is bent around massive clusters of galaxies. The amount of lensing observed often exceeded the mass that could be attributed to the visible components, suggesting a significant amount of invisible matter present. Additionally, measurements of the cosmic microwave background radiation provided further evidence for dark matter. The patterns of temperature fluctuations in the CMB serve as a snapshot of the universe in its early phases and can be interpreted to reveal information about the total matter content of the universe. The data indicated that dark matter makes up a substantial portion of the universe's total mass energy content. These compelling observations collectively led scientists to conclude that ordinary matter alone could not explain the gravitational phenomena observed in galaxies and galaxy clusters. Dark matter was posited as a crucial component of the universe, influencing structure formation and the dynamics of cosmic systems, although its exact nature remains one of the significant mysteries in contemporary astrophysics. Gravitational lensing and galaxy rotation curves are two crucial observational phenomena providing compelling evidence for the existence of dark matter. Gravitational lensing occurs when the light from a distant object, such as a galaxy, passes near a massive object, like a galaxy cluster, on its way to Earth. The gravitational field of the massive object warps the space around it, causing the light to bend, much like how a lens focuses light. This effect can create multiple images of the same distant object, distort the appearance of background galaxies, or form rings known as Einstein rings. When astronomers analyze the amount of lensing, they find that the observed bending of light often exceeds what can be accounted for based on the visible mass of the intervening galaxy cluster. The discrepancy suggests that there is additional unseen mass, dark matter, contributing to the gravitational pull and influencing how light is bent. Galaxy rotation curves provide complementary evidence for dark matter through the study of the motion of stars within galaxies. When scientists measure the rotational speeds of stars at various distances from the galactic center, they expect to see a curve that decreases with distance, similar to the way planets in the solar system behave. However, observations show that stars far from the center of galaxies orbit at high velocities that do not decrease as expected. This flat rotation curve indicates that there is much more mass present in the galaxy than what can be observed, as the visible matter, stars, gas, and dust, is insufficient to explain the high rotational speeds. The presence of dark matter, which forms an extended halo around galaxies, is posited to account for the gravitational forces needed to maintain these velocities at large radii. Together, these two lines of evidence reveal a consistent picture of a universe dominated by dark matter. Gravitational lensing highlights the presence of unseen mass in galaxy clusters, while galaxy rotation curves indicate that galaxies themselves are enveloped in extensive dark matter halos. Both phenomena not only support the existence of dark matter, but also challenge our understanding of the universe, prompting ongoing research into its properties and interactions. The leading candidates for dark matter particles encompass several theoretical possibilities, with the most prominent being weakly interacting massive particles, or WIMPs. WIMPs are hypothesized particles that would have mass in the range of a few giga-electronvolts to several hundred giga-electronvolts. They interact via the weak nuclear force and gravity, making them difficult to detect but plausible as dark matter components. Theoretical frameworks like supersymmetry, which extends the standard model of particle physics, predict the existence of WIMPs, particularly the lightest supersymmetric particle, which could serve as a dark matter candidate. Another candidate gaining attention is axions, hypothetical elementary particles proposed in a theory to resolve the strong CP problem in quantum chromodynamics. Axions are predicted to have extremely small masses and are expected to interact very weakly with ordinary matter. Their unique properties suggest that they could comprise a significant portion of dark matter, and researchers are actively seeking them through various detection methods, including searching for axion-induced electric fields in strong magnetic fields. Sterile neutrinos are also considered as potential dark matter candidates. Unlike regular neutrinos, sterile neutrinos do not interact via the weak force but may influence gravity. They could be produced in the early universe and might provide a mechanism to explain the discrepancies observed in galaxy formation and structure. Their properties could allow them to account for both warm and cold dark matter scenarios, making them versatile candidates. Finally, primordial black holes are another intriguing possibility. These black holes could have formed in the very early universe due to density fluctuations rather than from collapsing stars. If they exist with masses ranging from that of small asteroids to several solar masses, they could contribute to the overall dark matter content of the universe. The quest to identify and characterize these candidates is ongoing, with experiments and observations dedicated to uncovering the elusive nature of dark matter. Each of these candidates offers intriguing insights into the composition of our universe, inviting extensive research to understand their viability and interactions. Dark energy refers to the mysterious force that is driving the accelerated expansion of the universe. It is believed to make up about 70% of the total energy density of the cosmos. Unlike dark matter, which exerts gravitational attraction, dark energy appears to work against gravity, causing galaxies to move away from each other at an increasing rate. This leads to the perplexing realization that while gravity should slow down the universe's expansion, dark energy instead accelerates it. The discovery of dark energy can be traced back to observations made in the late 20th century. In the mid-1990s, two independent teams of astronomers, using Type Ia supernovae as standard candles, sought to measure the rate of expansion of the universe. They expected to find that the expansion was slowing down due to gravitational effects. However, to their surprise, they found that the light from these distant supernovae was dimmer than anticipated. This unexpected dimness indicated that the supernovae were farther away than they should be if the expansion was slowing. Instead, they suggested that the universe's expansion was actually accelerating. These findings were groundbreaking and suggested that something unseen was driving this acceleration, leading to the formulation of the dark energy concept. The equation of state for dark energy relates its density to pressure, implying that it has a negative pressure that counteracts the attractive force of gravity on cosmic scales. While various theories have been proposed to explain dark energy, including the cosmological constant, quintessence, and modifications to general relativity, no definitive explanation has been reached. Subsequent observations and studies, including measurements of the cosmic microwave background radiation and galaxy clustering, have confirmed the presence of dark energy and its effects on the universe's evolution. The study of dark energy remains one of the most significant challenges in modern cosmology, as understanding its nature could offer profound insights into the ultimate fate of the universe and the fundamental laws governing its expansion. Dark energy plays a crucial role in the dynamics of the universe's expansion. Discovered through observations of distant supernovae, this mysterious force accounts for roughly 70% of the total energy content of the cosmos. While gravity acts to pull matter together, dark energy exerts a counteracting pressure, pushing galaxies apart and accelerating the rate of expansion. The concept of dark energy challenges our understanding of physics, as it behaves differently than any known form of matter or energy. The fabric of space itself is stretching due to this enigmatic energy, causing galaxies that were once moving at a steady pace to increasingly recede from one another. As the universe ages, this expansion is expected to accelerate further, leading to a scenario where distant galaxies become unreachable, hidden behind an ever-expanding cosmic horizon. One fascinating aspect of dark energy is that while it is uniform and smooth on large scales, it is not fully understood how it originated or what its true nature might be. Some theories propose it could be related to the energy of empty space, while others suggest it might be a property of gravity at cosmic scales. This interplay between dark energy and the expansion of the universe raises profound questions about the ultimate fate of everything we know. As scientists continue to investigate the mysteries of dark energy through various means, including sophisticated telescopes and cosmic surveys, the quest to understand this force brings us closer to unveiling the secrets of our universe. With each discovery, They refine our understanding of the cosmos and our place within it, all the while confronting the astonishing reality that most of the universe remains an enigma. A black hole is a region in space where the gravitational pull is so intense that nothing, not even light, can escape from it. This phenomenon occurs when a massive star exhausts its nuclear fuel. As the star runs out of energy, it can no longer support itself against the force of gravity. The core collapses under its own weight, leading to an incredibly dense object with an intense gravitational field. Black holes can be categorized into three main types: stellar black holes, supermassive black holes, and intermediate black holes. Stellar black holes form when massive stars, those typically more than 20 times the mass of our Sun, reach the end of their life cycle. They explode in a catastrophic event known as a supernova, ejecting their outer layers while their core collapses into a black hole. Supermassive black holes, on the other hand, lurk at the centers of galaxies and can have masses equivalent to millions or even billions of suns. The exact mechanism behind their formation remains a topic of ongoing research, with theories suggesting they could form from the merging of smaller black holes or from the collapse of massive gas clouds. Another intriguing type is the intermediate black hole, which sits in mass between stellar and supermassive black holes. These remain somewhat elusive, with fewer confirmed examples, and their formation processes are still being explored. Regardless of type, all black holes share an event horizon, the boundary beyond which nothing can escape. Once crossed, all information about the matter that falls into a black hole is lost to the outside universe, leading to fascinating discussions about the nature of information and the laws of physics. The study of black holes not only challenges our understanding of gravity and spacetime, but also inspires countless inquiries into the fundamental workings of the universe. Each discovery brings insights into the life cycles of stars, the behavior of matter under extreme conditions, and the very nature of reality. As scientists illume the mysteries hidden within black holes, we inch closer to understanding some of the most profound questions in cosmology. Black holes can be classified into several distinct categories, each characterized by their mass and formation processes. The primary types include stellar black holes, supermassive black holes, and intermediate black holes, with each type exhibiting unique properties and playing specific roles within the universe. Stellar black holes are formed when massive stars, typically more than 20 times the mass of our Sun, exhaust their nuclear fuel. As these stars enter the final stages of their life cycle, they undergo a supernova explosion, shedding their outer layers while their cores collapse under gravity, creating a dense singularity where the gravitational pull is overwhelming. These black holes generally have masses ranging from a few to a few dozen solar masses. Supermassive black holes, as their name suggests, are significantly larger, boasting masses that can reach millions or even billions of solar masses. These black holes are thought to reside at the centers of most galaxies, including our Milky Way. Their formation is still a subject of research, but theories suggest they could form from the gradual merging of smaller black holes or from the collapse of massive gas clouds in the early universe, accumulating mass over billions of years through the gravitational attraction of surrounding material. Intermediate black holes are a lesser-known category, sitting between stellar and supermassive black holes in terms of mass. These black holes range from hundreds to thousands of solar masses and are believed to form through the merging of smaller black holes or through the collapse of massive star clusters. Detecting and studying intermediate black holes poses challenges, as they are not as prevalent and are difficult to observe. Understanding these various types of black holes enhances our knowledge of the cosmos and the life cycle of stars. Each category illustrates different aspects of gravitational physics and the evolution of galaxies, providing a complex tapestry of phenomena that continue to intrigue astronomers and cosmologists. Supermassive black holes play a crucial role in the formation and evolution of galaxies. Residing at the centers of most galaxies, including our Milky Way, these colossal entities exert a tremendous gravitational influence on their surrounding regions. Their presence not only affects the motion of stars and gaseous materials within galaxies, but also influences the overall structure and behavior of galaxies over cosmic time. One significant impact of supermassive black holes is their contribution to the regulation of star formation. During various stages of a galaxy's evolution, the intense gravitational pull of a supermassive black hole can trigger the accumulation of gas and dust, leading to bursts of star formation in the surrounding area. However, if the black hole becomes extremely active, radiating immense energy in the form of jets and radiation from accreting material, it can heat up the gas in the galaxy, preventing it from cooling and collapsing into new stars. This feedback loop can consequently moderate star formation rates, shaping the galaxy's evolution. Additionally, supermassive black holes directly shape the dynamics of galaxies through their gravitational influence. As galaxies merge or interact, the supermassive black holes at their centers usually coalesce as well. This merger process can lead to the emission of gravitational waves, ripples in spacetime, which carry information about these explosive cosmic events. The interactions between these black holes and their host galaxies impact the orbits of stars, potentially redistributing stellar material and altering the overall morphology of the galaxy. Furthermore, the study of supermassive black holes offers essential insights into the history and evolution of the universe itself. By observing their growth patterns and relations to galaxy formation, scientists can gather key clues about the conditions present in the early universe. As we delve deeper into understanding these magnificent cosmic phenomena, we unveil the intricate web that links supermassive black holes to the origins and transformations of galaxies across time and space, revealing the interconnectedness of the universe. The event horizon of a black hole serves as the critical boundary between the black hole's interior and the outside universe. Once crossed, this point represents the limit beyond which nothing, neither matter nor light, can escape the intense gravitational pull of the black hole. This unique characteristic is what grants black holes their mysterious nature. For an observer located outside the event horizon, the signals emitted by objects approaching this boundary would take increasingly longer to reach them. As an object nears the event horizon, it appears to slow down and fade from view due to gravitational time dilation, a phenomenon predicted by Einstein's theory of general relativity. From the outside perspective, the infalling object never truly crosses the event horizon, but appears to hover at the boundary, gradually becoming dimmer and more red-shifted until it is no longer visible. However, for the object falling into the black hole, the experience is quite different. As it crosses the event horizon, it enters a realm where the gravitational forces become extreme. The curvature of space-time is so steep that once an object surpasses this threshold, it is inexorably drawn toward the singularity, the point at the center of the black hole where density is thought to become infinite. The laws of physics as we know them begin to break down in this environment, leading to challenges in understanding the fundamental nature of reality. The event horizon also raises intriguing questions about information and its preservation in the universe. When matter falls into a black hole, it seems to carry information about its state with it, leading to discussions about whether this information is lost, a dilemma known as the black hole information paradox. This paradox has sparked intense debate in the scientific community, touching on the fundamental principles of quantum mechanics and gravity. As physicists explore these mysteries, the event horizon remains a critical focus for unraveling the complexities of black holes and the nature of cosmic existence. Detecting and studying black holes is a complex endeavor, as they do not emit light and cannot be observed directly. Instead, astronomers rely on indirect methods to infer their presence and understand their properties. One of the primary techniques involves observing the effects of a black hole's immense gravitational pull on nearby matter. This is often done by examining the motion of stars and gas clouds in close proximity to a suspected black hole. By analyzing the orbits of these objects, scientists can estimate the mass of the black hole, even if it cannot be seen. Another method involves looking for the emissions produced when matter falls into a black hole. As gas and dust spiral toward the event horizon, they form an accretion disk, heating up to extreme temperatures and emitting X-rays and other forms of radiation before crossing the event horizon. Astronomers utilize space-based telescopes designed to capture high-energy emissions, revealing important information about black holes and their accretion processes. Instruments like the Chandra X-ray Observatory and the Event Horizon Telescope have made significant advancements in also capturing images of the region surrounding supermassive black holes. Gravitational waves, ripples in spacetime caused by the collision and merger of black holes, are another groundbreaking method for studying these enigmatic objects. Detectors such as the Laser Interferometer Gravitational Wave Observatory have enabled scientists to observe and analyze these events, providing insights into the properties of black holes and their formation. The detection of gravitational waves has opened a new frontier in astronomy, allowing researchers to explore the dynamics of black hole mergers and understand the population of stellar black holes in the universe. Finally, theoretical models and simulations play a significant role in the study of black holes. These models help scientists conceptualize how black holes interact with their environment and evolve over time. By combining observational data with theoretical frameworks, astronomers piece together the immense puzzle of black holes, expanding our understanding of the cosmos and challenging our fundamental concepts of physics. As technology advances and new detection methods emerge, the mysteries surrounding black holes continue to be unveiled, deepening our comprehension of the universe. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions. Formed from the core collapse of a dying star that is between 8 and 20 times the mass of our Sun, these stellar remnants represent one of the most extreme states of matter in the universe. After exhausting their nuclear fuel, the outer layers of the star are ejected in a brilliant explosion, while the core collapses under the force of gravity, resulting in a neutron star. The key feature of neutron stars is their extraordinary density. When a star collapses, protons and electrons from its atomic structure combine to form neutrons, resulting in a core primarily composed of tightly packed neutrons. This compression produces a star with a mass greater than the Sun, but compressed into an area no larger than a city. The density is so high that a sugar cube-sized amount of neutron star material would weigh about as much as a mountain on Earth, making neutron stars among the densest objects in the universe. Neutron stars can also exhibit other fascinating behaviors and characteristics. One of the most remarkable features is their rapid rotation. Many neutron stars, known as pulsars, are found to spin several times each second, emitting beams of radiation that sweep across space. If the beam points towards Earth, we observe periodic pulses of light, similar to a cosmic lighthouse. These pulsars offer valuable insights into the extreme physics operating in such dense environments. The study of neutron stars not only expands our understanding of stellar evolution, but also provides insights into fundamental physics, such as the behavior of matter under extreme conditions. The existence of neutron stars challenges our knowledge of nuclear physics and the forces that govern interactions at the subatomic level. As researchers continue to explore these fascinating cosmic objects, they unlock more secrets about the life cycles of stars and the fundamental structure of matter in the universe. Neutron stars are among the densest objects in the universe, with densities that surpass those of ordinary matter and even that of atomic nuclei. To put this into perspective, a neutron star typically has a mass greater than that of the Sun, yet it is compressed into a sphere with a radius of only about 10 kilometers. This staggering density means that a single teaspoon of neutron star material would weigh in the realm of several billion tons, equivalent to the weight of an entire mountain on Earth. In comparison, Earth's density is approximately 5.5 grams per cubic centimeter, while the density of a neutron star can exceed hundreds of millions of grams per cubic centimeter. Such extreme values arise because the core of a neutron star is predominantly composed of neutrons packed closely together under immense gravitational pressure. This contrasts sharply with other astronomical objects, such as white dwarfs, which are the remnants of less massive stars and have densities about 100,000 times that of the Sun, but are considerably less dense than neutron stars. Additionally, neutron stars outstrip the density of black holes, as they represent an earlier stage in stellar evolution. Once a neutron star undergoes further collapse, particularly under additional mass or certain conditions, it may transition into a black hole. While black holes possess a singularity at their core, where density is thought to become infinite, neutron stars maintain a defined structure that reflects a balance between gravitational forces and the repulsive forces between neutrons. Understanding the immense density of neutron stars illuminates not only the processes of stellar evolution, but also the behavior of matter under extreme conditions. Research into these dense objects offers valuable insights into fundamental questions about the nature of nuclear interactions, the forces that govern matter, and the intricate workings of the universe on both large and small scales. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation, which can be observed as regular pulses when the beam is directed toward Earth. These cosmic lighthouses form from the remnants of massive stars that have undergone supernova explosions, resulting in incredibly dense neutron stars with intense magnetic fields and rapid rotation rates. As pulsars rotate, their magnetic fields create powerful electromagnetic forces. The combination of the neutron star's rapid rotation and its strong magnetic field causes charged particles, such as electrons, to accelerate along the magnetic field lines, which are typically tilted relative to the axis of rotation. This acceleration generates beams of radiation, which can encompass a range of wavelengths, including radio, X-rays, and gamma rays. If these beams periodically sweep past Earth, observers detect them as pulses of radiation, leading to the characteristic lighthouse-like effect. The periods at which pulsars emit these signals can vary significantly, with some pulsars spinning several hundred times per second, while others may emit at much lower frequencies. The regularity of their pulses can be remarkably precise, making pulsars valuable tools for scientific research. For instance, the timing of these pulses can help astronomers study various phenomena, including the effects of gravitational waves and the curvature of spacetime. Some pulsars have unique features that enhance their study. Millisecond pulsars, for example, are older pulsars that rotate incredibly quickly, often hundreds of times per second. Such rapid rotation is usually the result of accretion of material from a companion star, which transfers angular momentum and leads to faster spinning. By studying these cosmic phenomena, scientists gain deeper insights into the fundamental laws of physics, the behavior of matter under extreme conditions, and the intricate interplay between stellar evolution and the celestial mechanics governing the universe. Studying neutron star mergers offers profound insights into several fundamental aspects of astrophysics and cosmology. When two neutron stars collide, they produce an incredibly energetic event that sends waves of gravitational energy rippling through spacetime. Observing these mergers allows scientists to directly measure gravitational waves, providing a new way to explore the universe and test the predictions of general relativity. One of the most significant revelations from neutron star mergers is their role in the synthesis of heavy elements. During the violent collision, immense amounts of energy are released, and conditions are ripe for nucleosynthesis, the process by which atomic nuclei are formed. Specifically, these events are believed to be responsible for creating many of the heavier elements found in our universe, including gold, platinum, and other heavy metals. By analyzing the electromagnetic radiation emitted before and after the merger, astronomers can gain valuable information about the processes that produce these elements. Additionally, neutron star mergers provide key insights into the nature of matter under extreme density and pressure. The merger process involves a complex interplay of nuclear forces, and studying the resulting kilonova, an astronomical event that occurs following the merger, offers a glimpse into the behavior of nuclear matter in such extreme conditions. Observing the emission spectra from kilonovae allows researchers to explore the properties of nuclear interactions and refine their understanding of the strong force that binds protons and neutrons together. Furthermore, these mergers help address fundamental questions related to the expansion rate of the universe. With the detection of gravitational waves associated with neutron star mergers, scientists can measure the distances to these events more accurately. Combined with the redshift data from accompanying electromagnetic signals, this information contributes to our understanding of the Hubble constant, the rate of expansion of the universe, and can help resolve existing disparities in measurements from different cosmic sources. The study of neutron star mergers is a rich field that extends our understanding of gravity, nuclear physics, cosmic element formation, and the evolution of the universe. Each discovery not only enriches our knowledge of astrophysics, but also deepens our appreciation for the intricate processes that shape the cosmos. Magnetars are a unique subclass of neutron stars characterized by their extraordinarily strong magnetic fields, which can be over 1,000 times more powerful than those of typical neutron stars. While both regular neutron stars and magnetars are remnants of massive stars that have undergone supernova explosions, the defining feature of a magnetar is its intense magnetic field, which can reach strengths of around 1,000 million teslas. This is approximately 1,000 times stronger than the magnetic field of a regular neutron star. The strong magnetic fields of magnetars significantly influence their behavior and the phenomena associated with them. For instance, these immense magnetic forces can cause dramatic bursts of energy. Magnetars are known to emit X-rays and gamma rays in short and intense bursts, a phenomenon that can happen on timescales of just milliseconds to hours. These bursts can be so powerful that they are detectable across vast distances, providing astronomers with valuable information about their properties and environments. In contrast, while regular neutron stars can also emit radiation, they do not exhibit the same explosive behavior and are often observed as pulsars with stable rotation periods. Moreover, the energy released by a magnetar's magnetic field can cause starquakes, akin to earthquakes on Earth, which occur due to the shifting of the star's crust under extraordinary magnetic pressure. These starquakes can result in brief but intense emissions of high-energy radiation. Regular neutron stars do not experience the same kind of magnetic-induced seismic activity, as their fields are generally weaker and more stable. Both magnetars and regular neutron stars serve as important laboratories for studying fundamental physics, particularly the behavior of matter under extreme conditions. The investigation of magnetars helps scientists explore the strong nuclear force, magnetic field interactions, and the nature of matter at unprecedented densities. Understanding the differences between these fascinating stellar objects further enhances our comprehension of the life cycles of massive stars and the complex phenomena that arise in the universe. Detecting exoplanets or planets outside our solar system involves various sophisticated techniques that allow scientists to infer their presence, characteristics, and even their atmospheres. One of the most prevalent methods is the transit method, which observes the periodic dimming of a star's light caused by a planet passing in front of it. When a planet transits, it blocks a fraction of the star's light, leading to a measurable decrease in brightness. By analyzing the light curve, the graph of a star's brightness over time, astronomers can determine the planet's size, orbital period, and distance from its star. Another powerful technique is the radial velocity method, also known as the Doppler method. This approach detects changes in the star's light spectrum due to the gravitational pull of an orbiting planet. As the planet orbits, it causes the star to wobble slightly, leading to shifts in the star's light due to the Doppler effect. When the star moves toward us, its light shifts to the blue end of the spectrum, and when it moves away, it shifts to the red. By measuring these shifts, scientists can infer the presence of a planet and estimate its mass. Direct imaging is another method employed in exoplanet detection, which involves capturing actual images of exoplanets. While challenging due to the overwhelming brightness of stars, advanced techniques such as coronography or starshade technology allow astronomers to block out starlight, making it possible to spot the faint light emitted or reflected by planets. This method can also provide valuable information about the planet's atmosphere and even surface conditions. Additionally, Gravitational microlensing offers a unique way to detect distant exoplanets. When a massive object, such as a star, passes in front of a more distant star, its gravitational field can bend and magnify the light from the background star. If a planet orbits the foreground star, it can create additional light variations that indicate the presence of the planet. This method is especially useful for discovering exoplanets that are far from their parent stars. These various detection methods have expanded our understanding of planetary systems beyond our own, revealing a diverse array of exoplanets with different sizes, compositions, and orbital characteristics. As technology advances and new telescopes are developed, the search for exoplanets continues to uncover new worlds and expands our knowledge of the potential for life beyond Earth. A wide variety of exoplanets have been discovered, revealing a fascinating spectrum of planetary types that challenge our understanding of planetary formation and migration. One of the most common categories is the so-called hot Jupiters. These gas giants, similar in size to Jupiter, orbit very close to their parent stars, resulting in extremely high surface temperatures. Their proximity to their stars leads to swift orbital periods, often completing an orbit in just a few days. The discovery of hot Jupiters was surprising, as it challenges traditional theories of planetary formation, which suggested that gas giants should form further out in the colder regions of a protoplanetary disk. Another major type of exoplanet is the super-Earth. These are rocky planets with a mass larger than Earth's but smaller than that of Neptune. Super-Earths can vary significantly in composition, with some potentially harboring substantial atmospheres and even conditions favorable to life. Their existence expands the understanding of planetary systems and raises intriguing questions about the potential habitability of these worlds. Additionally, there are mini-Neptunes, which are smaller than Neptune but larger than Earth, exhibiting characteristics of both gas giants and terrestrial planets. These planets often have thick atmospheres with a mix of gas and ice components, which makes them distinct from super-Earths. The abundance of mini-Neptunes in discovered planetary systems has prompted ongoing research into their formation and atmospheric dynamics. Terrestrial planets, similar to Earth and Venus, have also been found, although they are more challenging to detect due to their smaller sizes. Some of these rocky exoplanets reside within their star's habitable zone, where conditions might allow for liquid water to exist on their surfaces. This has made them particularly intriguing in the search for extraterrestrial life. The diversity of exoplanets discovered so far underscores the complexity and variety of planetary systems across the universe. Each new finding provides essential clues about the processes of planet formation, migration, and the potential for life beyond our solar system. As technology advances and future missions are launched, astronomers are eager to explore this rich landscape of exoplanets even further, uncovering new worlds and expanding our understanding of the cosmos. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. This zone is crucial for the search for extraterrestrial life because water is considered a key ingredient for life as we know it. The distance from a star where a planet can maintain liquid water depends on the star's size and temperature. Thus, the habitable zone varies between different star systems. Identifying planets within the habitable zone allows scientists to focus their search for life on those worlds that might have the right conditions for ecosystems to develop. However, being in the habitable zone does not guarantee that a planet is habitable. Other factors also come into play, such as atmospheric composition, surface pressure, and geological activity. For instance, a planet too close to its star may be uninhabitable due to scorching temperatures and excessive radiation, while a planet too far may be too cold, resulting in frozen surfaces. Understanding the habitable zone is important for several reasons. First, it helps refine the criteria for selecting exoplanets for further study. While planets within this zone are prime candidates for hosting life, researchers also consider the possibility of life existing in extreme conditions, such as subsurface oceans on icy moons or planets with significant greenhouse effects. This broadens the search for life beyond just the habitable zone. Moreover, Studying the characteristics of planets within the habitable zone provides insights into planetary climates and atmospheres, essential for assessing potential habitability. By examining factors like the presence of greenhouse gases, magnetic fields, and the planet's geological history, scientists can better understand what makes a planet suitable for life. The study of the habitable zone is thus a cornerstone in astrobiology, guiding researchers as they seek to answer fundamental questions about the existence of life beyond Earth. Searching for biosignatures on exoplanets involves identifying chemical and physical indicators that suggest the presence of life or biological processes. Astronomers employ various methodologies to detect these signatures, utilizing advanced technology and analytical techniques to study the atmospheres and surface conditions of potential habitable exoplanets. One of the primary methods for detecting biosignatures is through spectroscopy, which involves analyzing the light spectra from a planet's atmosphere. When a planet transits in front of its star, some of the starlight passes through the planet's atmosphere, absorbing specific wavelengths depending on the atmospheric composition. Researchers look for certain gases that are considered potential biosignatures, such as oxygen, methane, carbon dioxide, and ozone. The presence of free oxygen, or a combination of gases like oxygen and methane, is particularly exciting, as these substances tend to react with each other and would require a continuous source to be maintained, suggesting biological processes. In addition to atmospheric analysis, scientists are also interested in surface conditions that might indicate the presence of life. For instance, detecting the presence of liquid water in environments such as oceans or lakes can signal the potential for biological activity. Remote sensing techniques, which involve observing planetary characteristics from afar, allow researchers to gather crucial information about surface features, temperature, and geological activity. Furthermore, the study of exoplanets in their habitable zones enhances the potential to find biosignatures. By focusing on planets that orbit within the region where conditions might allow for liquid water and other life-supporting factors, scientists increase the likelihood of discovering signs of life. Evaluating planets for geological activity and assessing their magnetic fields can also provide insights into their ability to protect life from harmful cosmic radiation. As technology advances with new telescopes and instruments, such as the James Webb Space Telescope, the capacity to gather detailed data on exoplanet atmospheres and surfaces improves significantly. This enhanced capability positions researchers to better explore the fascinating possibility of life beyond Earth, driving the quest to uncover biosignatures that may fundamentally change our understanding of the universe and our place within it. Some of the most promising exoplanets for potential life lie within a region known as the habitable zone, where conditions might allow for liquid water to exist. One of the most notable candidates is Proxima Centauri b. This planet orbits the red dwarf star Proxima Centauri, which is located just over 4 light-years away from Earth. It is roughly the same size as our planet and sits comfortably within the habitable zone of its star, sparking interest in its potential to support life. Another intriguing exoplanet is Kepler-186f, which was discovered by NASA's Kepler Space Telescope. This planet is slightly larger than Earth and resides in the habitable zone of its star, Kepler-186. The interesting aspect of Kepler-186f is that it is part of a system with multiple planets, giving scientists the opportunity to study how planetary environments influence each other. Then there is TRAPPIST-1, a system that has 7 Earth-sized planets, 3 of which are located in the habitable zone. This system is particularly captivating because of the diverse range of environments that might exist across these worlds. Composed of a cool dwarf star, the TRAPPIST-1 system allows for the possibility that not just one, but multiple planets could potentially harbor conditions conducive to life. Additionally, there's LHS 1140b, an exoplanet located 41 light-years away from Earth that is considerably larger than our planet, but still within its star's habitable zone. It is a rocky world, and its specific characteristics excite scientists as they consider the potential for life. As technology advances, these intriguing worlds invite us to explore further, hoping to learn more about the myriad possibilities of life beyond our solar system. Stars begin their lives in vast clouds of interstellar gas and dust, primarily composed of hydrogen molecules. Over time, regions within these clouds can undergo gravitational collapse. Initially, small disturbances, such as shock waves from nearby supernovae, can trigger the collapse of denser regions within the cloud. As gravity pulls the gas and dust together, the material begins to clump into denser cores. As these cores become increasingly dense and compact, they heat up due to the pressure exerted on them. This stage is known as the protostar phase. During this time, the protostar absorbs surrounding material, which increases its mass and temperature. Eventually, when the temperature at the core reaches millions of degrees, nuclear fusion reactions commence, marking the birth of a new star. This fusion process involves hydrogen atoms combining to form helium, releasing immense amounts of energy in the process. It is noteworthy that not all the material in the surrounding cloud becomes part of the star. Some of it will form a rotating disk around the new star. This disk can eventually lead to the formation of planets, moons, and other celestial bodies. The outflow of material along the rotational axis of the star can also occur, resulting in powerful stellar winds that help clear out leftover gas and dust. The whole process of star formation can take millions of years, during which time a star gathers mass and evolves. As it reaches a stable phase on the main sequence of the Hertzsprung-Russell diagram, it enters a long period of luminosity where it spends the majority of its life shining brightly and creating the conditions necessary for life on nearby planets. Thus, the cycle of stellar birth not only shapes individual stars, but also the fate of entire solar systems. A star's lifespan and ultimate fate are primarily determined by its mass. The mass of a star influences its core temperature, pressure, and the rate at which it consumes its nuclear fuel. More massive stars burn their hydrogen fuel significantly faster than smaller stars, leading to a shorter lifespan. While a star like the Sun has a life expectancy of about 10 billion years, a massive star could live for merely a few million years before depleting its nuclear fuel and evolving into its later stages. As a star progresses through its life cycle, it undergoes various transformations. Once a star exhausts its hydrogen supply in the core, it enters the red giant phase. During this period, the core contracts and heats up, prompting the surrounding hydrogen shell to ignite and begin fusing into helium. This process creates an extended outer envelope that can result in dramatic changes in brightness and size. Ultimately, the star expels its outer layers, forming a planetary nebula, while the core remains behind as a white dwarf. For massive stars, the end of the life cycle is far more explosive. Once they have fused heavier elements in their cores, they may undergo a supernova explosion. This cataclysmic event occurs when the core collapses under gravity, causing a rebound effect that blasts the outer layers into space. What remains after the supernova can become a neutron star or even collapse further into a black hole, depending on the mass of the core. The journey of a star from its birth to its demise is significantly shaped by its initial mass. While smaller stars may end their lives gently, leaving behind white dwarfs, massive stars meet a spectacular end, leading to the formation of exotic remnants like neutron stars or black holes. This complex interplay of mass and energy defines the life cycle of stars and their influence on the cosmos. Supernovae play a vital role in the chemical enrichment of the universe by dispersing heavy elements into the surrounding space. When a massive star reaches the end of its life, it undergoes a dramatic explosion known as a supernova. In this event, the core of the star collapses, and the outer layers are expelled at incredible speeds. The energy released is so immense that it creates conditions allowing for the fusion of lighter elements into heavier ones during the final stages of the star's life. Before the supernova occurs, elements such as helium, carbon, nitrogen, and oxygen are produced and accumulated in the star's core through nuclear fusion. When the supernova explosion happens, it not only sends these elements hurtling into space, but also creates even heavier elements up to iron through rapid neutron capture processes called R-process nucleosynthesis. Elements heavier than iron, like gold and uranium, can be formed during these explosive events as well. This results in a rich array of elements being scattered across the universe. As the stellar material mixes with the interstellar medium, the expelled elements become part of the gas and dust clouds that eventually give rise to new stars and planetary systems. The chemical compositions of these new celestial bodies can be significantly altered by the presence of heavy elements from previous supernovae. This cycle of stellar birth, death, and rebirth continuously enriches the universe with a diverse range of chemical elements essential for the formation of planets and the emergence of life. Consequently, supernovae not only contribute to the distribution of elements throughout the cosmos, but they also serve as cosmic recycling processes. Through the violent deaths of stars, the universe becomes a tapestry of elemental diversity, influencing the chemical makeup of future generations of stars, planets, and life itself. Each supernova occurrence plays a crucial part in the ongoing narrative of cosmic evolution. Brown dwarfs are fascinating celestial objects that occupy a unique space between the largest planets and the smallest stars. They are often described as failed stars because they form in a similar way to stars but lack sufficient mass to initiate hydrogen fusion in their cores. Typically, a brown dwarf has a mass ranging between 13 to 80 times that of Jupiter, making them more massive than gas giant planets, but not massive enough to sustain the nuclear reactions that characterize true stars. The primary difference between brown dwarfs and stars lies in their core processes. While stars ignite hydrogen fusion and can sustain this process for billions of years, brown dwarfs do not reach the necessary core temperatures and pressures. As a result, they primarily generate energy through a process called deuterium fusion in their early stages and later by burning lithium. However, these processes are short-lived. Once the deuterium and lithium are depleted, brown dwarfs gradually cool over time without a continuous energy source like stars. Brown dwarfs are often found in regions where stars are formed, and they can emit faint light primarily in the infrared spectrum, making them difficult to detect with standard optical telescopes. Because of their low luminosity, many brown dwarfs remain hidden in the shadows of their more brilliant stellar counterparts. Remarkably, their existence challenges our understanding of the spectrum of objects in the universe, leading astronomers to explore the criteria that define stars versus planets. Scientists study brown dwarfs to gain insights into the formation and evolution of celestial bodies, helping to bridge the gap between full-fledged stars and planetary systems. By uncovering the characteristics of these enigmatic objects, we expand our knowledge of the vast diversity of the cosmos. Binary and multiple star systems form through processes similar to those that create single stars, but with notable differences that allow multiple stars to coalesce in close proximity. These systems typically arise from giant molecular clouds, where regions of gas and dust experience gravitational instabilities. When a dense region within one of these clouds collapses, it can fragment into two or more clumps, each of which may become a separate star. This fragmentation often results from turbulence within the cloud, and the specific conditions during formation determine whether the fragments will ultimately form a binary or a multiple star system. As these stars begin their lives, they can interact gravitationally with each other. In a binary star system, the two stars are in a mutual orbit, creating a complex dynamical relationship. Their gravitational pull affects each other's evolution, leading to phenomena such as mass transfer when one star evolves faster than the other. This mass transfer can significantly alter the star's structure and behavior, potentially leading to explosive events in cases where one star becomes a red giant and spills material onto its companion. In systems with more than two stars, interactions become even more intricate. The dynamics of multiple stars can lead to hierarchical structures, where a pair of stars orbits one or more additional stars. These relationships are influenced by gravitational interactions, which can result in changes in orbits over time. The evolutionary paths of these stars can vary widely. Some might end their lives as supernovae, while others could become white dwarfs, neutron stars, or black holes. The presence of multiple stars can also affect planet formation, as the gravitational interactions can complicate the orbits of any planets that form within the system. The study of binary and multiple star systems reveals crucial insights into stellar formation, evolution, and the mechanisms that govern the dynamics of celestial objects. Understanding these systems helps astronomers explore a diverse array of star types and behaviors, shedding light on how stars and the potential planetary systems around them interact and evolve over time. Galaxies form and evolve through a complex evolutionary process that begins shortly after the Big Bang. Initially, the universe was a hot, dense sea of particles, but as it expanded and cooled, small fluctuations in density allowed regions of gas and dark matter to attract one another through gravity. Over time, these gravitational pulls caused gas clouds to clump together, forming the first stars. As these early stars ignited, they began to fuse hydrogen into heavier elements, contributing to the chemical enrichment of the surrounding gas. The process of galaxy formation is often described in two key stages: the collapse of matter into proto-galaxies and the accretion of material. The first galaxies, known as proto-galaxies, emerged from massive clouds of gas that underwent gravitational collapse. There, star formation was intense, and the radiation from these newly formed stars heated the surrounding gas, causing turbulence and aiding the formation of more stars. Over time, gravity continued to pull in more gas and dark matter, leading to growth and the merging of smaller proto-galaxies into larger structures, a process known as hierarchical clustering. As galaxies evolve, they undergo a series of transformations that shape their structure and content. Interactions and mergers between galaxies can lead to significant changes. When galaxies collide, they can trigger bursts of star formation, alter their shapes, or even form elliptical galaxies from the merger of two spiral galaxies. The dynamics of both regular and irregular galaxies are profoundly influenced by these interactions, and the distribution of dark matter plays a key role in governing their gravitational interactions. Over billions of years, galaxies continue to evolve, influenced by factors such as star formation rates, supernova feedback, and the presence of supermassive black holes at their centers. The balance between gas inflow, star formation, and gas outflow driven by various processes, including active galactic nuclei feedback, determines the rate at which galaxies change and can influence the overall morphology of the galaxy. Studying galaxy formation and evolution helps astronomers piece together the grand tapestry of the universe, revealing the intricate relationships between galaxies, stars, and the dark matter that binds them. Galaxies are classified into several distinct types based on their shape, structure, and formation processes. The main categories include spiral galaxies, elliptical galaxies, irregular galaxies, and lenticular galaxies. Each type exhibits unique characteristics that reflect its formation history and the processes occurring within it. Spiral galaxies, such as the Milky Way and the Andromeda Galaxy, are characterized by their flat, rotating disks that contain stars, gas, and dust. They typically have well-defined spiral arms that wind outward from the center. The presence of young, bright stars and ongoing star formation in these arms creates a striking contrast with the older, redder stars found in the central bulge. Spiral galaxies also host supermassive black holes at their cores, which can influence the dynamics and evolution of the galaxy as a whole. Elliptical galaxies differ significantly in shape, ranging from nearly spherical to elongated. They are primarily composed of older red stars and typically have little to no gas and dust, which results in minimal star formation. Many elliptical galaxies are found in clusters, where gravitational interactions can lead to the depletion of gas as stars merge and collide. This type of galaxy is often associated with the later stages of galaxy evolution, where they may have grown through mergers with other galaxies. Irregular galaxies, as their name suggests, lack a regular structure or defined shape. They appear chaotic and are typically rich in gas and dust, resulting in high rates of star formation. The irregular shapes of these galaxies often arise from gravitational interactions with nearby galaxies or previous mergers, which can distort their initial formation. Examples of irregular galaxies include the Large and Small Magellanic Clouds, which are satellite galaxies of the Milky Way. Lenticular galaxies represent a category that bridges the characteristics of spiral and elliptical galaxies. They possess a central bulge similar to elliptical galaxies, but also feature a disk component. However, lenticular galaxies show limited spiral structure and low rates of star formation compared to spiral galaxies, indicating a transitional phase in their evolutionary path. The presence of a significant bulge and a disk allows for some similarities to both types. The diverse array of galaxy types provides fascinating insights into the processes of stellar formation, evolution, and the cosmic dance of gravitational interactions. Understanding these differences helps astronomers unravel the history of galaxies and their roles in the larger cosmic tapestry. Galaxy collisions and mergers play a crucial role in shaping the evolution of galaxies, often leading to dramatic and transformative changes. When galaxies come close to one another, their mutual gravitational forces can create intricate dynamics that lead to interactions between them. During these encounters, various phenomena occur, including tidal forces that distort their shapes and trigger bursts of star formation in regions where gas clouds collide and compress. One significant outcome of galaxy mergers is the alteration of a galaxy's structure. For example, when spiral galaxies collide, the interaction can lead to the formation of an elliptical galaxy, which is characterized by a more rounded and featureless appearance. This transformation occurs as the gravitational effects of the merger disrupt the orderly disk structures of the spirals, allowing gravitational energy to reshape the stars and gas into a more homogeneous distribution. Thus, the fate of colliding galaxies often hinges on their relative masses, velocities, and orientations at the time of encounter. Mergers also play a vital role in enriching the interstellar medium with heavier elements. When galaxies collide, supernovae occurring in both galaxies can inject massive amounts of heavy elements into the surrounding gas. This enriched material can serve as the building blocks for new stars, furthering the cycle of stellar evolution. In cases where the merger involves a massive galaxy with a supermassive black hole at its center, the merger can also stimulate agitated activity in the black hole, leading to the formation of active galactic nuclei, which can emit significant amounts of radiation. Furthermore, the effects of these collisions may not only be limited to individual galaxies, but can also influence their groups and clusters. When several galaxies merge, they can trigger a series of cascading interactions throughout the cluster, affecting the orbits of other galaxies and the distribution of dark matter. The intricate gravitational dance of these cosmic entities underscores the importance of galaxy mergers and collisions in the broader context of galactic evolution, contributing significantly to the ongoing story of the cosmos. Galaxy clusters are large-scale structures that consist of hundreds to thousands of galaxies bound together by gravity. These clusters are among the largest known gravitationally bound structures in the universe and serve as vital laboratories for studying cosmic evolution, dark matter, and the large-scale structure of the universe. A typical cluster contains not only galaxies but also vast amounts of hot gas and dark matter, which account for a significant portion of the cluster's mass. The formation of galaxy clusters involves the processes of cosmic structure formation that unfolded after the Big Bang. Over billions of years, small density fluctuations in the early universe began to grow through gravitational attraction. Dark matter played a crucial role in this process, as its gravitational influence helped pull in gas and matter. Regions with slightly higher density attracted more mass, leading to the gradual merging of smaller structures into larger ones. This hierarchical clustering process results in the formation of galaxy clusters from smaller groups and superclusters. As galaxy clusters form, the interaction and merging of galaxies within them can lead to significant evolutionary changes. Gravitational interactions can result in galaxy mergers, causing transformations that alter the morphologies of the galaxies involved. Additionally, the hot gas within galaxy clusters, often observed as X-ray emitting plasma, can also affect the galactic dynamics. Critically, the interplay between galaxies and the surrounding hot gas contributes to star formation rates and the ultimate destinies of galaxies within the cluster. Clusters can also reveal important information about dark matter and the geometry of the universe. Observations of galaxy clusters, especially through gravitational lensing effects, provide crucial insights into the distribution of dark matter, illustrating the unseen content that dominates the mass-energy budget of the universe. Measuring the properties of clusters allows astronomers to trace the evolution of structure in the cosmos, helping to refine models of cosmic evolution and improve our understanding of fundamental processes that govern the universe's behavior. Galaxy clusters serve as powerful tools for studying dark matter and dark energy due to their unique properties and the gravitational effects they exhibit. Since dark matter does not emit, absorb, or reflect light, it cannot be observed directly. However, its influence is evident through the behavior of galaxies and the hot gas within clusters. By observing how these components behave under the gravitational pull of unseen mass, astronomers can infer the presence and distribution of dark matter. One primary method of studying dark matter in galaxy clusters is through gravitational lensing, which occurs when light from distant galaxies is bent around the massive gravitational field of a galaxy cluster. This bending distorts the images of background galaxies, creating arcs and multiple images. By analyzing the extent of this lensing effect, astronomers can map the distribution of dark matter within and around the cluster, revealing insights into how mass is distributed in these huge cosmic structures. This technique has provided compelling evidence for the existence of dark matter and has contributed to our understanding of its behavior in the universe. Galaxy clusters also play a critical role in the study of dark energy, which is hypothesized to be responsible for the accelerated expansion of the universe. Observations of galaxy clusters provide valuable data points for understanding the relationship between mass and the expansion rate of the universe. By examining the number and distribution of clusters over time, researchers can compare how the properties of clusters have evolved and help refine models of cosmic expansion. The relationship between the rate of cluster formation and the influence of dark energy can reveal important truths about its properties and contributions to the universe's overall dynamics. Moreover, the cosmic microwave background radiation serves as a complementary tool to study both dark matter and dark energy. Through detailed measurements of fluctuations in this ancient light, astronomers can glean insights into the large-scale structure growth, including how galaxy clusters are distributed. By integrating these methods, researchers create a more comprehensive understanding of the interplay between dark matter and dark energy, paving the way for a deeper exploration of the universe's fundamental composition and its ultimate fate. Cosmic voids are vast, largely empty regions of space that contain far fewer galaxies than typical areas of the universe. These voids can be immensely large, with diameters ranging from tens of millions to hundreds of millions of light-years. Despite their apparent emptiness, cosmic voids play a key role in shaping the large-scale structure of the universe and influencing galaxy formation and distribution. The formation of cosmic voids is closely tied to the process of cosmic inflation that occurred shortly after the Big Bang. During this early period, quantum fluctuations in density caused variations in matter distribution. Over billions of years, gravity began acting on these density fluctuations, leading to the clumping of matter in some regions, while other areas experienced less gravitational attraction. As matter gathered into filaments and clusters, the regions where fewer galaxies formed grew into the voids we observe today. In the cosmic web model, matter organizes itself into a network of filaments, sheets, and clusters, leaving large regions devoid of significant material. As galaxies formed and clustered together due to gravitational forces, the space between these clusters expanded into cosmic voids. The dynamics within these voids are characterized by lower density and a slower rate of gravitational attraction, allowing them to grow larger over time as they essentially become fossils of the universe's evolution. The study of cosmic voids offers valuable insights into the behavior of dark energy and dark matter, as their structures can help researchers understand the large-scale dynamics of the universe. The observation of these voids, including their shapes, sizes, and distributions, contributes to our understanding of the overall fabric of the cosmos. Consequently, Cosmic voids are an important component in the quest to unravel the mysteries of the universe and its evolution through time. Cosmic voids significantly influence the distribution of matter in the universe by shaping the overall architecture of the cosmic web, which is composed of filaments, clusters, and sheets where galaxies reside. These vast, largely empty regions have lower densities compared to the denser areas filled with galaxies and galaxy clusters. As a result, voids create a kind of framework within which matter is organized. The presence of cosmic voids leads to a gravitational effect that contributes to the dynamics of galaxies and clusters. In areas near a void, the gravitational pull from surrounding matter is altered, affecting the motion and behavior of galaxies located at the edges of these voids. While galaxies within these dense regions may experience strong gravitational interactions, those on the outskirts of voids tend to move away from them, leading to peculiar motions and potentially influencing their formation and evolution. Moreover, voids can also impact star formation rates in their vicinity. The relatively low density within voids means less available gas to create new stars compared to the denser environments of clusters. Consequently, galaxies located within cosmic voids may exhibit lower star formation rates and different evolutionary paths than their counterparts in denser regions. This phenomenon contributes to a diverse range of galaxy types and properties throughout the universe. The study of cosmic voids and their effects further enhances our understanding of dark matter and dark energy, as these structures can provide insights into how the universe's expansion is influenced. Analyzing the shapes, sizes, and distributions of cosmic voids allows astronomers to refine models of cosmic evolution and the underlying principles of structure formation. Altogether, cosmic voids play a critical role in the fabric of the universe, shaping the distribution of matter and influencing the dynamics of galaxies over cosmic time. Cosmic filaments are vast, thread-like structures made up of galaxies, gas, and dark matter that form a significant part of the cosmic web, which is the large-scale structure of the universe. These filaments connect clusters of galaxies and can stretch across hundreds of millions of light-years, creating a network that resembles a giant spider's web. Within this intricate arrangement, filaments act as the pathways along which matter accumulates, leading to the formation and distribution of galaxies. The cosmic web, composed of filaments, walls, and voids, represents the largest scale organization of matter in the universe. After the Big Bang, gravitational forces began to pull matter together, with quantum fluctuations in the density of matter leading to the clustering of particles. Over time, these clumps formed the filaments of the cosmic web, where dark matter played a crucial role by providing the gravitational scaffolding. Most visible galaxies are found along these filaments, while large, empty regions, known as cosmic voids, exist between them. The formation of cosmic filaments is closely linked to the phenomenon of hierarchical clustering, where smaller structures merge to create larger ones. As galaxies and other matter coalesce along the filaments, they form galaxy clusters at their intersections, while lower density regions emerge in the spaces between. This interconnectivity not only facilitates the movement of galaxies, but also influences the exchange of gas and dark matter, making it integral to star formation processes and the evolution of galaxies. Studying cosmic filaments helps astronomers gain insights into the fundamental forces shaping the universe. The characteristics, dynamics, and evolution of these filaments shed light on the behavior of dark matter and dark energy, providing a clearer understanding of the forces that govern the cosmos. By observing the cosmic web and its components, researchers can unravel the story of the universe's architecture and its ongoing evolution. Galaxies and galaxy clusters are distributed along cosmic filaments in a pattern that reflects the underlying structure of the cosmic web. This distribution is primarily driven by gravitational forces, where matter accumulates in regions of higher density, leading to the formation of clusters and groups at the intersections of the filaments. The filaments themselves are characterized by a relatively higher density compared to surrounding cosmic voids, which serve as expansive, empty spaces. As galaxies form and evolve, their locations are influenced by the gravitational pull exerted by nearby filaments. This leads to a process known as large-scale structure formation, where galaxies appear more clustered along these filaments while being sparsely distributed in the vast voids between them. As a result, the filaments typically host a rich tapestry of galaxies, often exhibiting a diverse range of types, from spiral and elliptical galaxies to irregular ones. The concentrations of galaxies along these structures provide insights into how different environments affect galaxy evolution and behavior. Galaxy clusters, which are among the largest gravitationally bound structures in the universe, are often found at the nodes or junctions of these filaments. These clusters serve as the densest areas within the cosmic web, where the interplay of gravitational attraction leads to significant clustering. The presence of these large clusters can also influence the environments of surrounding galaxies, dictating star formation rates and the retention of gas. Furthermore, the distribution of galaxies along cosmic filaments plays a pivotal role in shaping the overall dynamics of the universe. As filaments connect clusters, they facilitate the flow of material, allowing gas and dark matter to move between different regions. This interconnectedness shapes the processes of galaxy formation, star formation, and even the cycling of gases within clusters. Understanding how galaxies and clusters are laid out along these filaments gives astronomers a clearer picture of the evolution of the universe and the forces that govern the large-scale structure of cosmic matter. Cosmic voids and filaments reveal critical insights into the architecture of the universe. Voids, which are vast expanses of space with very few galaxies, make up about 80% of the universe's volume. They act like cosmic deserts, surrounded by dense clusters of galaxies. These voids help scientists understand the gravitational forces that shape the large-scale structure of the cosmos, giving us clues about how matter is distributed and how it evolved over billions of years. Filaments, on the other hand, are the long, thread-like structures that connect these galaxies and galaxy clusters. They form the backbone of the cosmic web and are composed mostly of dark matter and gas. By examining the properties of these filaments, researchers can learn about the conditions of the early universe, the influence of dark matter, and the processes that contributed to galaxy formation. The existence of these interconnected structures suggests a universal pattern governed by gravitational attraction, indicating that the universe prefers a certain organization. Studying the relationship between voids and filaments also sheds light on the expansion of the universe. As the cosmos expands, galaxies are drifting away from each other, and the matter distribution affects this rate of expansion. Voids, being less populated, expand more rapidly, while the regions filled with galaxies tend to exert greater gravitational forces, slowing down their expansion. This interplay between different cosmic structures helps scientists refine their models of dark energy, the mysterious phenomenon accelerating the universe's expansion. The intricate dance of voids and filaments has broader implications for understanding cosmic evolution. Observing how galaxies cluster and avoid other regions expands our knowledge of how they formed and interacted over time. These phenomena give rise to questions about the fundamental nature of matter and energy in the universe, highlighting the allure of cosmology and unraveling the cosmos's deepest mysteries. Gravitational waves are ripples in the fabric of spacetime that are produced by some of the universe's most violent and energetic processes, such as the collision and merger of black holes or neutron stars. Albert Einstein first predicted these waves in his general theory of relativity a century ago, describing how massive objects influence the geometry of spacetime around them. When these massive bodies accelerate, they generate waves that travel outward at the speed of light, carrying information about their origins. The first ever detection of gravitational waves occurred on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, more commonly known as LIGO. This groundbreaking event marked an extraordinary achievement in physics and astronomy. LIGO employs precise laser technology to measure minute changes in distance caused by passing gravitational waves. As these waves stretch and compress spacetime, they alter the distances between test masses located kilometers apart, allowing scientists to capture fleeting signals that reveal the occurrence of cosmic events. The specific event detected by LIGO was the merger of two black holes, approximately 1.3 billion light-years away from Earth. As they spiraled closer together before merging, they generated gravitational waves that caused ripples across spacetime, which LIGO successfully identified. The signal lasted only a fraction of a second, but it was powerful enough to demonstrate the profound impact of these waves emanating from such distant and violent cosmic phenomena. The discovery of gravitational waves opened a new window into the universe, allowing scientists to observe objects that were previously invisible to traditional telescopes. This has led to a deeper understanding of black holes, neutron stars, and the processes governing their interactions. Furthermore, it represents the emergence of gravitational wave astronomy, paving the way for future explorations of the universe's most enigmatic and energetic events. Gravitational waves provide an innovative means of observing the universe, supplementing conventional electromagnetic observations such as those made with visible light, radio waves, and X-rays. Unlike traditional forms of astronomy that rely on light emitted or absorbed by celestial objects, gravitational waves offer a direct glimpse into the cataclysmic events occurring in the cosmos. These waves carry with them vital information about the dynamics of their sources, allowing scientists to study phenomena that may be undetectable through other methods. One of the key advantages of gravitational waves is that they can penetrate dense cosmic environments that might obscure light. For instance, when two black holes or neutron stars collide, the resulting gravitational waves travel through the universe unfettered by obstacles like gas or dust. This means that even if these events are invisible to electromagnetic observations, they can still be detected, providing a unique opportunity to explore the behaviors of these extreme objects and their interactions. Moreover, gravitational waves can reveal details about their sources that are not accessible through traditional techniques. For example, when scientists detected the merging of two neutron stars, they not only captured the gravitational waves, but also were able to observe the electromagnetic radiation emitted during the event. This multimodal approach allowed researchers to gather a comprehensive understanding of the merger, leading to significant breakthroughs in understanding the origin of heavy elements like gold and platinum. As gravitational wave astronomy continues to evolve, it paves the way for numerous discoveries about the universe's most extreme and elusive phenomena. The ability to capture and analyze these waves enhances our understanding of the cosmos, from the nature of black holes and neutron stars to the fundamental physics of gravity itself. This new observational frontier broadens the scope of astronomical research and challenges our comprehension of the universe's structure and evolution. Several types of cosmic events generate detectable gravitational waves, primarily those involving extremely massive and accelerating objects. One of the most notable sources is the merger of black holes. When two black holes spiral towards each other, their immense gravitational pull creates ripples in spacetime that propagate outward. As they collide and merge, they produce powerful gravitational waves that can be detected by observatories like LIGO and Virgo. Another significant source of gravitational waves involves neutron stars, which are incredibly dense remnants of supernova explosions. When two neutron stars orbit each other and eventually merge, they release a tremendous amount of energy, generating gravitational waves as they collide. This type of event is particularly interesting because it often produces electromagnetic radiation as well, allowing scientists to observe the same phenomenon through different wavelengths, leading to a more comprehensive understanding of the event. Additionally, more exotic events such as the collision of black holes and neutron stars can also generate detectable waves. The dynamics of these interactions may provide vital insights into the properties of both types of compact objects, including their masses and spins. These systems can yield valuable information about the fundamental traits of matter in extreme environments. Furthermore, other phenomena, such as the rapid rotation of highly asymmetric supernova explosions, can produce gravitational waves, although these signals are often more challenging to detect. The growing field of gravitational wave astronomy is expanding our knowledge of these events, offering emerging opportunities to explore situations that previously remained hidden from traditional astronomical observations. As technology and observational capabilities improve, the list of detectable cosmic phenomena will likely continue to expand. Gravitational wave detectors, like the Laser Interferometer Gravitational Wave Observatory, operate using a principle known as interferometry. Detectors utilize highly sensitive instruments that can measure minute changes in distance caused by passing gravitational waves. LIGO, for instance, features two long arms arranged in an L shape, each extending several kilometers. Laser beams are split and sent down these arms, reflecting off mirrors at the far ends. When a gravitational wave passes through the detector, it slightly distorts spacetime, causing alterations in the distances that the laser beams travel. One arm may stretch while the other contracts, resulting in a slight change in the time it takes for the light to travel back and forth. These minute fluctuations, often on the order of 1,000th the diameter of a proton, are what the detector measures. To capture and analyze these tiny variations, the system employs interferometry. When the two laser beams return to the point where they were initially split, they combine, creating an interference pattern. This pattern is sensitive to any changes in the path length of the laser beams, allowing researchers to detect gravitational waves. By analyzing these changes, scientists can infer the properties of the waves and, consequently, the nature of the cosmic events that produce them. Advanced technologies are crucial for enhancing the sensitivity of gravitational wave detectors. State-of-the-art equipment, including high-power lasers and ultra-stable mirrors, enables scientists to detect even the faintest signals. Environmental noise reduction techniques, such as suspending mirrors in a vacuum, are essential to ensuring that only gravitational wave signals are observed, minimizing interference from other sources. As these technologies continue to advance, the capabilities of gravitational wave detectors will expand, leading to an even deeper understanding of the universe. Gravitational wave observations have provided groundbreaking insights into the dynamics of the universe and the behavior of extreme cosmic phenomena. Since the first detection in 2015, scientists have confirmed the existence of binary black hole mergers, revealing a diverse population of black holes that often defy previous expectations regarding their masses and spins. This has led to a better understanding of how black holes form and evolve, offering clues about the intricate processes occurring in stellar evolution. The detection of gravitational waves from neutron star mergers has been particularly significant. In 2017, the merger of two neutron stars not only produced a gravitational wave signal, but also coincided with electromagnetic signals observed across the spectrum. This multimodal observation provided a wealth of information about the event, including the production of heavy elements such as gold and platinum, which had previously remained a mystery. Such findings have illuminated the processes of nucleosynthesis in the universe, enhancing our comprehension of the origins of elements. Beyond specific events, gravitational waves are challenging our understanding of fundamental physics. The precise measurements allow researchers to test predictions of general relativity under conditions of extreme gravity. Any deviations from the expected results can hint at new physics or guide the search for phenomena like dark matter. The study of gravitational waves opens new avenues for exploring the properties of spacetime and the fundamental forces that govern the universe. Additionally, gravitational wave observations are transforming the landscape of astronomy itself. As researchers continue to detect and analyze these waves, the field of gravitational wave astronomy is emerging. This new era enables the exploration of a variety of cataclysmic events, offering a way to study the universe that complements traditional observations. The ongoing discoveries promise to yield even more exciting revelations about the fundamental nature of the cosmos in the years to come. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. These particles primarily consist of protons, but they can also include heavier nuclei, electrons, and other subatomic particles. When cosmic rays enter the Earth's atmosphere, they collide with atoms and molecules, producing cascades of secondary particles that can be detected at ground level or by satellites in space. Their origins remain a topic of active research, with several potential sources identified throughout the universe. The vast majority of cosmic rays originate from sources within our own galaxy, the Milky Way. Supernova explosions are a significant contributor, as these stellar deaths create shock waves that accelerate particles to immense speeds. These high-energy environments are prime candidates for cosmic ray production. Furthermore, other sources such as pulsars, rapidly spinning neutron stars that emit beams of radiation, also contribute to the cosmic ray population by accelerating particles through their powerful magnetic fields. Beyond our galaxy, some high-energy cosmic rays are believed to originate from active galactic nuclei, which are regions surrounding supermassive black holes. As material falls into these black holes, it can be accelerated and ejected at relativistic speeds, leading to the creation of cosmic rays. Additionally, gamma-ray bursts, among the most energetic explosions in the universe, may also be capable of generating these high-energy particles. The study of cosmic rays is crucial, as it not only enhances our understanding of particle physics and astrophysical processes, but also poses challenges for our atmospheric and technological systems. While the Earth's magnetic field shields us from many of these high-energy particles, some can penetrate the atmosphere and reach the surface, raising questions about their effects on human health and technology. With ongoing research, scientists aim to uncover more about the origins and implications of cosmic rays, deepening our understanding of the universe and the fundamental interactions of matter. Cosmic rays interact with Earth and its atmosphere in several significant ways, influencing both our planet's environment and the living organisms that inhabit it. When high-energy cosmic rays enter the atmosphere, they collide with atomic nuclei, producing a cascade of secondary particles, including muons, pions, and other charged particles. These secondary particles can penetrate deep into the atmosphere, with some even reaching the Earth's surface. The effects of this interaction can vary widely, impacting everything from atmospheric chemistry to biological processes. One of the notable impacts of cosmic rays is their contribution to atmospheric ionization. As they collide with atmospheric molecules, cosmic rays help create ions, which can influence cloud formation and weather patterns. This ionization contributes to the natural background radiation found on Earth and plays a role in the cloud condensation nuclei, which are essential for cloud formation. Some researchers are investigating whether variations in cosmic ray intensity might correlate with climate fluctuations, although this remains an area of ongoing debate and study. In terms of biological effects, cosmic rays pose a potential risk to living organisms. While the Earth's atmosphere and magnetic field provide significant shielding against high-energy particles, some cosmic rays manage to penetrate and can cause ionization in cells and genetic material. This exposure has been linked to various health concerns, including an increased risk of cancer due to DNA damage. Astronauts and airline pilots who experience higher levels of cosmic ray exposure due to their altitude are often monitored for radiation exposure to assess potential health risks. Additionally, cosmic rays have implications for technological systems. These high-energy particles can disrupt electronics and communication systems, particularly in satellites and high-altitude flights. They can lead to transient errors known as single-event upsets in computer memory or even damage sensitive electronic components. As our reliance on technology continues to grow, understanding and mitigating the effects of cosmic rays becomes increasingly important to ensure the reliability and safety of various systems. Thus, cosmic rays play a multifaceted role in influencing Earth's atmosphere, biological health, and technological infrastructure. Gamma-ray bursts are among the most powerful and energetic events observed in the universe, releasing immense amounts of energy in the form of gamma radiation. They last from a few milliseconds to several hours and can emit more energy in a few seconds than the Sun will emit over its entire lifetime. These bursts are typically detected as brief flashes of gamma rays, often from distant galaxies, making them essential subjects of study in high-energy astrophysics. The exact mechanisms behind gamma-ray bursts are still an active area of research, but they are generally classified into two categories: long-duration bursts and short-duration bursts. Long-duration gamma-ray bursts, lasting more than 2 seconds, are thought to be associated with the collapse of massive stars. When a massive star exhausts its nuclear fuel, it can undergo a supernova explosion, leading to the formation of a neutron star or black hole. During this process, highly focused jets of relativistic particles are produced, creating the intense gamma radiation characteristic of these bursts. Short-duration gamma-ray bursts, lasting less than 2 seconds, are believed to arise from the merger of compact objects, specifically neutron stars or black holes. When two neutron stars orbit each other and eventually collide, the resulting cataclysmic event can release vast amounts of energy, including gamma rays. This theory was bolstered by simultaneous observations of gravitational waves and electromagnetic radiation from a neutron star merger in 2017, providing a remarkable example of how these bursts can arise from such catastrophic cosmic events. The study of gamma-ray bursts is vital for understanding the extreme conditions present in the universe. Their immense energies and distances provide insights into stellar evolution, the behavior of matter under extreme gravity, and the origins of heavy elements. Observing these bursts also sheds light on the early universe, as many gamma-ray bursts originate from the regions where star formation is most active, offering a glimpse into the processes that shaped galaxies over cosmic time. Studying ultra-high-energy cosmic rays involves a combination of ground-based and space-based observatories, as well as advanced detection techniques designed to capture these rare and high-energy particles. Ultra-high-energy cosmic rays are particles that exceed an energy threshold of around 1 billion electron volts, significantly higher than typical cosmic rays. Their rarity makes their study challenging, requiring extensive collaborations and sophisticated methods to detect and analyze them. Ground-based observatories, such as the Pierre Auger Observatory in Argentina and the Telescope Array in the United States, are crucial for studying ultra-high-energy cosmic rays. These facilities utilize an approach known as extensive air shower detection. When an ultra-high-energy cosmic ray enters the Earth's atmosphere, it collides with air molecules, producing a cascade of secondary particles known as an air shower. These showers can cover large areas and can be detected by a network of ground sensors. By observing the characteristics of these showers, such as their density and distribution, scientists can infer the properties of the original cosmic ray, including its energy and composition. In addition to ground-based efforts, space-based observatories like the Alpha Magnetic Spectrometer and the Cosmic Ray Observatory play a role in gathering data on cosmic rays in a more direct manner. While these instruments primarily target lower-energy cosmic rays, they complement ground-based observations by offering insights into cosmic ray composition and behavior beyond the atmosphere. Space missions help to measure the charge, momentum, and energy of cosmic rays, providing more comprehensive data on their origins. The study of ultra-high-energy cosmic rays also involves theoretical modeling and simulations to interpret the observation data effectively. Understanding the sources of these high-energy particles, whether they come from supernova remnants, active galactic nuclei, or other astrophysical phenomena, requires integrating observational findings with theoretical frameworks. Continued advancements in detector technology, data analysis techniques, and collaborative efforts among researchers worldwide will enhance our capacity to unravel the mysteries surrounding ultra-high-energy cosmic rays and their roles in the universe. Cosmic rays serve as crucial messengers from the most energetic events in the universe, providing valuable insights into astrophysical processes and phenomena. Their high-energy nature indicates that they originate from violent and extreme environments, allowing researchers to study the underlying mechanisms at play in these cosmic events. By analyzing cosmic rays, scientists can gain a deeper understanding of sources like supernovae, active galactic nuclei, and gamma-ray bursts. One of the key insights from cosmic rays relates to their composition and distribution. Variations in the elemental makeup of cosmic rays can reveal details about their origins. For instance, helium nuclei, Heavier elements or even heavier nuclei can indicate specific sources or acceleration processes occurring in massive stellar explosions or in the vicinity of supermassive black holes. By studying these elemental ratios and energy spectra, scientists hope to identify the conditions that lead to the production of cosmic rays and track their journey through space. Moreover, cosmic rays can help illuminate the processes of particle acceleration in the vicinity of powerful astrophysical phenomena. The mechanisms by which these particles obtain their immense energies, often surpassing those achieved in human-made particle accelerators, can be explored through observations of cosmic rays. Understanding how particles are accelerated to ultra-high energies can shed light on the interaction of matter and radiation in extreme environments, enhancing our knowledge of fundamental physics. Another important role of cosmic rays is in probing the interstellar medium and the conditions of space between stars. As cosmic rays propagate through galaxies, they ionize gas and affect the chemistry of the interstellar medium. This interaction with matter allows researchers to study cosmic ray transport mechanisms and the influence of cosmic rays on star formation processes. Thus, cosmic rays are not only representative of extreme cosmic events, but also provide insights into the larger framework of the universe, revealing the interconnectedness of various cosmic processes and the fundamental nature of the cosmos. The multiverse hypothesis proposes that our universe is just one of many, possibly an infinite number, of distinct universes that exist simultaneously. Depending on the version of the multiverse theory, these universes may have varying physical laws, constants, and dimensions, leading to vastly different realities. The concept challenges the traditional view of self-contained universes and has gained attention in both scientific and philosophical discussions regarding the nature of reality. Several lines of reasoning and theories contribute to the multiverse hypothesis. One influential concept comes from cosmology, particularly the theory of cosmic inflation. According to this theory, an extremely rapid expansion occurred in the early universe, leading to a uniform and flat cosmos. However, this inflation process could be happening continually in different regions of space, leading to multiple pockets of spacetime where each pocket evolves into an individual universe with its own properties. This form of the multiverse is referred to as the inflationary multiverse. Another perspective on the multiverse comes from the realm of quantum mechanics, specifically the many worlds interpretation. This interpretation suggests that every quantum event results in the branching of the universe into different outcomes, creating parallel realities for each possible outcome. As a result, every decision or random event may give rise to a new universe where every scenario plays out, leading to a vast and complex web of realities. The multiverse hypothesis raises profound questions about the nature of existence, the uniqueness of our universe, and the laws of physics that govern it. While the idea is compelling and offers explanations for certain fine-tuning observations, such as the precise conditions necessary for life, it remains largely speculative. Current scientific methods struggle to provide empirical evidence for the existence of other universes, making the multiverse hypothesis a topic of rigorous debate within the scientific community. As research in cosmology continues, exploring the implications of the multiverse may enrich our understanding of the fundamental nature of reality and the universe itself. The idea of parallel universes arises from the many worlds interpretation of quantum mechanics, a theoretical framework proposed by physicist Hugh Everett III in the 1950s. This interpretation aims to address the inherent ambiguities and seemingly paradoxical outcomes of quantum phenomena, particularly the nature of measurement. In classical quantum mechanics, particles exist in a state of superposition, meaning they can simultaneously occupy multiple states until observed. The act of measurement collapses this superposition into one observable outcome. The many worlds interpretation suggests a different perspective on this process. Instead of collapsing a superposition into a single state, it posits that all possible outcomes of a quantum event occur simultaneously but in separate, branching universes. For example, consider a simple quantum experiment, such as a photon passing through two slits. Instead of producing a single observable spot on a screen upon measurement, the photon takes both paths simultaneously, creating two distinct realities, one where the photon goes through the first slit and another where it passes through the second. Thus, the universe splits into branches corresponding to each possible outcome. This branching process doesn't just occur in thought experiments. It extends to every quantum interaction, including everyday decisions and events. Consequently, the many worlds interpretation implies that every choice or probabilistic event leads to the creation of new parallel universes, where every conceivable scenario plays out. In this framework, an infinite number of alternate realities exist, where every possible state and decision effectively manifests in its own universe. While the many worlds interpretation has intriguing implications for our understanding of reality, it also raises critical questions about the nature of existence and the limits of our observational capabilities. Currently, there is no empirical evidence to confirm or deny the existence of these parallel universes, making the concept both fascinating and speculative. As quantum mechanics continues to challenge our intuitions about the universe, the idea of parallel universes encourages us to think beyond the confines of our single reality and consider the myriad possible outcomes that could arise from the fundamental rules of quantum physics. The inflationary multiverse theory is a cosmological model that builds upon the concept of cosmic inflation, an extremely rapid expansion of the universe believed to have occurred just after the Big Bang. This theory posits that various regions of spacetime underwent inflation at different times and rates, leading to the creation of multiple independent pocket or bubble universes. Each of these universes can have distinct physical properties, constants, and laws of physics, resulting in a vast multiverse. Cosmic inflation was initially proposed to address certain perplexing observations about the universe, such as its uniformity and the distribution of galaxies. The rapid expansion would have smoothed out any irregularities, leading to a homogeneous and isotropic universe. However, the inflationary multiverse theory takes this a step further by suggesting that the inflationary process is not a singular event, but an ongoing and potentially infinite one, occurring in various regions of an overarching spacetime. Within this framework, each bubble universe forms when a region of space undergoes inflation and eventually stops inflating, leading to the creation of a unique universe with conditions distinct from others. For example, one bubble might develop the physical laws we observe today, while another bubble could have entirely different constants, possibly even allowing for different types of matter or fundamental forces. This vast array of universes could explain observations that seem fine-tuned for life, suggesting that we find ourselves in one of the many bubbles where conditions happen to be suitable for the emergence of life. One of the compelling implications of the inflationary multiverse theory is that it addresses some challenges in understanding why our universe has the specific parameters it does. Instead of assuming that our world is unique, the theory suggests that numerous other universes exist with various configurations, and we merely reside in one that seems optimally set for life. Although the idea is compelling, it is also highly speculative and presents challenges in terms of testability and empirical validation. Current scientific efforts continue to explore the ramifications of this theory, contributing to our broader understanding of the cosmos and our place within it. The potential existence of a multiverse poses significant challenges for empirical testing due to its inherently speculative nature. However, several theoretical approaches and observable phenomena may offer indirect ways to explore the multiverse hypothesis. These methods primarily rely on distinguishing features or consequences that could arise from multiverse scenarios. One approach involves searching for observable signatures of other universes, particularly in the cosmic microwave background radiation, which is the remnant radiation from the Big Bang. If our universe is one of many, irregularities or specific patterns in the cosmic microwave background might reveal collisions or interactions with neighboring bubble universes. Researchers would look for characteristic anomalies, such as unexpected temperature fluctuations or peculiar alignment in the cosmic background, that could hint at the presence of other universes. Another avenue for investigation centers on the fine-tuning problem. The physical constants and laws of our universe appear meticulously adjusted to allow for the existence of life. The multiverse hypothesis might explain this fine-tuning by suggesting that numerous universes exist, with only a fraction capable of supporting life. If researchers can find evidence that certain constants vary in ways that align with multiverse predictions, it could provide indirect support for the existence of multiple universes. Additionally, advancements in particle physics and our understanding of fundamental forces may also provide insights. Experiments at high-energy particle colliders, such as the Large Hadron Collider, can explore theoretical frameworks that incorporate multiverse concepts. If we find evidence consistent with string theory or other models predicting extra dimensions or varying physical laws, it could support the multiverse theory indirectly. Lastly, while direct testing remains elusive, ongoing developments in astrophysics, cosmology, and quantum mechanics could lead to new observational techniques or theoretical insights that may shed light on the multiverse concept. As our understanding of the universe deepens, researchers continue to explore these complex ideas, and future advancements may reveal ways to gather evidence or make predictions that can either support or refute the multiverse hypothesis. The concept of a multiverse suggests that our universe is just one of many, each with its own distinct laws of physics and makeup. This idea fundamentally challenges how we approach our understanding of nature. If multiple universes exist, it raises questions about why our universe has the specific conditions it does, and whether these conditions are the result of chance or some underlying principle governing the nature of all universes. One significant implication of the multiverse theory is the possibility of different physical laws existing in other universes. This could mean that the constants we observe, such as the strength of gravity or the speed of light, could vary widely elsewhere. These variations could lead to entirely different forms of matter and even life that we cannot imagine. Such diversity would expand our scientific inquiries beyond the realm of our own universe, requiring new frameworks and models to comprehend the wider cosmos. Furthermore, the multiverse hypothesis raises profound philosophical questions about the nature of reality and our place in the cosmos. If countless universes exist, then the uniqueness of our own universe becomes a subject of contemplation. Are the laws of physics we study truly universal, or simply apparent in the context of our own universe? This broader perspective might challenge the ideas of determinism and predictability in physics, suggesting that phenomena observed in our universe could be just one version of reality among many possibilities. Embracing the multiverse concept could also spur advancements in theoretical physics, inspiring innovative ways to test and explore the boundaries of science. Researchers might develop new technologies or methodologies to probe the connections between different universes, leading to unforeseen discoveries. The acknowledgement of a multiverse, while still a speculative idea, opens avenues for both scientific and philosophical discourse, enriching our quest to understand the fundamental nature of existence itself. Einstein's theory of general relativity revolutionized our understanding of gravity by describing it not as a conventional force, but as a curvature of spacetime caused by mass and energy. According to this theory, massive objects, like planets and stars, warp the fabric of spacetime around them. Consequently, when smaller objects move within this curved spacetime, they follow paths determined by the shape of that curvature, which we perceive as gravitational attraction. This concept contrasts sharply with Isaac Newton's earlier model, where gravity was seen as an invisible force pulling objects toward one another. Instead, Einstein proposed that what we feel as gravity is actually the result of objects moving in straight lines within a curved spacetime. This idea helps explain why planets orbit stars and why light from distant stars bends when passing near massive objects, a phenomenon known as gravitational lensing. Einstein's equations of general relativity describe how mass and energy influence spacetime geometry. The more massive an object, the greater its effect on the curvature of spacetime. This interplay between matter and spacetime is beautifully illustrated by the analogy of a trampoline. When a heavy object is placed on the surface, it creates a dip, demonstrating how smaller objects roll toward it due to the dip in the fabric of the trampoline. The implications of general relativity extend beyond our local solar system. The theory predicts phenomena such as black holes, where spacetime becomes so curved that nothing, not even light, can escape. It also provides the foundation for understanding the expansion of the universe and the dynamics of galaxies. Through the lens of general relativity, gravity is not merely an invisible force, but a dynamic relationship between mass and the very structure of space and time itself. Spacetime is a fundamental concept that combines the three dimensions of space with the dimension of time into a single four-dimensional continuum. This idea, introduced by Albert Einstein, shifts our understanding of how these dimensions interrelate. Instead of viewing time and space as separate entities, spacetime presents them as interconnected, meaning that events cannot be fully described without considering both their location in space and their timing. In the framework of general relativity, mass and energy play a critical role in shaping the geometry of spacetime. When an object possesses mass, or when energy is present, it causes a distortion in this four-dimensional fabric. Einstein's equations illustrate how the presence of mass and energy dictates the curvature of spacetime. The greater the mass or energy of an object, the more pronounced the curvature it creates. As a result, the paths that other objects with less mass follow through spacetime can change, leading to the phenomenon we perceive as gravity. Conceptually, envision a heavy bowling ball placed on a stretched rubber sheet. The weight of the ball causes the sheet to sag, creating a dip in the surface. If smaller balls are rolled across the sheet, their trajectories curve towards the bowling ball due to the deformation of the rubber. This analogy helps visualize how mass affects the structure of spacetime. In addition to static masses, dynamic changes can also ripple through spacetime. For example, accelerated masses or changing energy distributions can generate gravitational waves, ripples in spacetime that travel at the speed of light. These waves reflect the movement and interactions of massive objects and provide further insight into the intricate relationship between mass, energy, and spacetime. Understanding spacetime opens the door to exploring complex cosmic phenomena and fundamental truths about the universe we inhabit. Testing general relativity involves a variety of methods that verify its predictions across different scenarios in the universe. One of the most famous tests occurred during a solar eclipse in 1917, when scientists observed the bending of starlight around the sun. This phenomenon, known as gravitational lensing, was predicted by Einstein's theory. Measurements revealed that light from stars closest to the sun appeared shifted, confirming that massive objects like stars and planets indeed curve spacetime. Another significant test of general relativity comes from observing the motion of planets and moons within our solar system. For instance, the precise measurement of the orbits of Mercury and other planets shows that they precess, or their orbits shift, due to gravitational influences. General relativity accurately predicts this precession, especially the additional shift observed in Mercury's orbit beyond what Newtonian physics could explain. Direct observations of gravitational waves provide some of the most exciting confirmations of general relativity. Detected by the LIGO Observatory for the first time in 2015, these ripples in spacetime are produced by violent cosmic events, such as the merging of black holes or neutron stars. The properties of gravitational waves match the predictions made by general relativity, allowing scientists to study cosmic events in unprecedented detail and further affirming the theory's validity. Additionally, experiments involving atomic clocks on satellites compared to those on Earth have demonstrated how gravity affects time. This phenomenon, called gravitational time dilation, shows that clocks positioned in stronger gravitational fields tick more slowly than those in weaker fields, consistent with Einstein's predictions. By continually testing general relativity through these diverse methods, scientists deepen their understanding of the universe and gain insights into its fundamental workings. Spacetime singularities are points in the fabric of spacetime where the gravitational forces become infinitely strong and the known laws of physics break down. At these singularities, Quantities like density and curvature are theorized to reach extreme values that defy computation or understanding. One of the most well-known types of singularity appears at the center of black holes, where matter is thought to be crushed into an infinitely small point. In the context of black holes, the singularity is surrounded by an event horizon, which is the boundary beyond which nothing, not even light, can escape the gravitational pull of the black hole. This creates a region of spacetime that is effectively disconnected from the rest of the universe, making it impossible for information or matter to return once it crosses this boundary. Within this extreme environment, the laws of general relativity, which describe gravity in terms of spacetime curvature, no longer provide answers, leading to a breakdown of our current understanding of physics. Beyond black holes, singularities may also arise in the early universe during the Big Bang. The leading cosmological models suggest that at the very beginning, the universe existed in an extremely hot, dense state, infinitely small in volume. The conditions in this singularity also challenge our current theories, as they would require a reconciliation between quantum mechanics and general relativity. This concept drives physicists to seek a unified theory that could adequately describe both domains. While singularities are theoretical constructs that emerge from our current understanding of gravity, they highlight the limitations of our models when it comes to extreme conditions. As scientists advance research in areas such as quantum gravity and string theory, the hope is to gain a clearer understanding of singularities and possibly unravel the mysteries of the universe itself. Each discovery could lead to a deeper comprehension of how the cosmos operates at both its grandest and most minuscule scales. Time dilation is a fascinating consequence of Einstein's theories of relativity, which asserts that time is not a constant, but rather can vary depending on relative speeds between observers or their positions in a gravitational field. There are two primary types of time dilation, one associated with relative velocity, known as special relativistic time dilation, and the other due to gravitational effects, termed gravitational time dilation. In the case of special relativistic time dilation, the faster an object moves relative to an observer, the slower time appears to pass for that object. This effect becomes more pronounced as the object approaches the speed of light. A classic example of this principle can be illustrated through thought experiments involving twin aging. If one twin journeys through space at a significant fraction of the speed of light while the other remains on Earth, the traveling twin will age more slowly when they reunite, due to the effects of time dilation. Gravitational time dilation, on the other hand, occurs in the presence of strong gravitational fields. According to general relativity, the stronger the gravitational pull, the more pronounced the time dilation effect. For instance, clocks that are situated closer to a massive object, like a planet or a star, tick more slowly compared to those further away. This phenomenon has practical implications. Clocks on satellites, which are further from the Earth's gravitational influence, tick slightly faster than identical clocks on the surface. We can observe the effects of time dilation in various real-world scenarios. One prominent example is in Global Positioning System, or GPS satellites. These satellites orbit the Earth at high speeds and experience less gravitational pull than those on the surface. Therefore, engineers must correct the satellite clocks for both types of time dilation to ensure that the GPS system provides accurate positioning data. Additionally, experiments using particle accelerators have confirmed time dilation by observing particles called muons. When accelerated to close to the speed of light, their decay times increase relative to stationary observers, offering direct evidence of the phenomenon. By affirming the significance of time dilation, we gain a richer understanding of the nature of time itself within our universe. Quantum mechanics plays a crucial role in our understanding of the universe by describing the behavior of matter and energy at the smallest scales. It provides a framework for understanding phenomena that classical physics cannot explain, such as the behavior of subatomic particles and the interactions between energy and matter. When studying the universe, quantum mechanics helps unveil the fundamental building blocks of reality and offers insights into processes at cosmic scales. One of the key applications of quantum mechanics in cosmology lies in the study of the early universe. Shortly after the Big Bang, the universe was in an extremely hot and dense state where quantum effects dominated. Quantum fluctuations during this period are believed to have seeded the large-scale structures we observe in the universe today, such as galaxies. This concept highlights the interplay between quantum mechanics and cosmic evolution, suggesting that the universe's structure is deeply rooted in quantum behaviors. Another significant area where quantum mechanics intersects with cosmology is in the investigation of black holes. According to quantum theory, particles can exist in multiple states until measured, leading to concepts such as superposition and entanglement. These ideas challenge our classical understanding of black holes. For instance, the black hole information paradox arises from the conflict between the principles of quantum mechanics and general relativity, particularly concerning how information that falls into a black hole is preserved or lost. Furthermore, the field of quantum field theory combines quantum mechanics with special relativity to describe fundamental interactions, such as electromagnetism and the weak and strong nuclear forces. This theory underpins our understanding of particle physics and informs models like the Standard Model, which encapsulates the known particles and their interactions. As researchers explore the universe's origins and its fundamental nature, the contributions of quantum mechanics are critical, driving advancements in theoretical physics and guiding investigations into phenomena such as dark matter, dark energy, and the unification of forces. Quantum entanglement is a striking phenomenon in quantum mechanics where two or more particles become linked in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. This means that when entangled particles are measured, the outcome of one measurement immediately determines the outcome of the other, a connection that seems to defy the classical understanding of information transfer, which should occur at or below the speed of light. Albert Einstein famously referred to this phenomenon as spooky action at a distance, highlighting its counterintuitive nature. Entanglement is observed in various experimental settings, reinforcing its importance in quantum mechanics. Its implications extend beyond individual particles to encompass larger systems and even intricate processes relating to cosmic phenomena. For instance, understanding how quantum entanglement operates is essential when exploring the behavior of particles in environments like those found within black holes or during the early moments of the universe, where quantum effects were paramount. The effects of quantum entanglement could also influence cosmological expansion and the nature of dark matter and dark energy. Some theoretical models suggest that entangled states might play a role in the universe's evolution, potentially offering insights into how entangled particles interact across vast distances. This could have implications for our understanding of cosmic coherence, a concept that refers to how quantum states remain correlated in large-scale systems, such as galaxies or clusters of galaxies. Moreover, quantum entanglement holds promise for advancing technologies such as quantum computing and quantum communication. As researchers harness the power of entangled states, the potential for revolutionary breakthroughs in information processing and secure communications emerges. In a broader context, investigating quantum entanglement within cosmic phenomena is critical to bridging the gap between quantum mechanics and general relativity, two pillars of modern physics that remain largely incompatible on their own. Exploring entanglement may ultimately lead to deeper insights into the fundamental nature of reality itself. Reconciling quantum mechanics with general relativity represents one of the most significant challenges in modern physics. These two foundational theories describe different aspects of the universe. Quantum mechanics excellently explains the behavior of particles at small scales, while general relativity describes the gravitational interaction and the curvature of spacetime on a grand scale. However, the fundamental principles of each theory are at odds, creating puzzles that scientists strive to solve. One of the primary difficulties arises from how gravity is treated in general relativity. In this framework, gravity is not a force but a result of the curvature of spacetime caused by mass and energy. Conversely, quantum mechanics typically deals with forces as interactions between particles. This conceptual divide makes it challenging to formulate a unified theory that incorporates both the probabilistic nature of quantum phenomena and the deterministic nature of general relativity. The search for such a unified theory has led to various approaches, one of which is string theory. This theoretical framework attempts to describe fundamental particles as one-dimensional strings rather than point-like entities. String theory inherently incorporates gravity by introducing a graviton, a hypothetical particle that mediates the gravitational force. Moreover, it suggests a vast landscape of possible universes, introducing additional dimensions that could help bridge the two frameworks. However, string theory remains an area of active research, with significant challenges related to experimental validation. Another path explored is loop quantum gravity, which aims to quantize spacetime itself. By treating spacetime as a network of discrete loops, this theory seeks to merge the principles of quantum mechanics with general relativity. It suggests that space has a granular structure at the smallest scales, potentially resolving issues linked to singularities found in black holes and the Big Bang. This approach emphasizes a quantum nature of spacetime rather than treating gravity solely as a geometric property. While these frameworks provide intriguing pathways toward unification, a complete reconciliation of quantum mechanics and general relativity is yet to be achieved. As researchers continue to probe the nature of black holes, cosmic expansion, and the very fabric of space and time, they inch closer to unveiling the deeper truths of our universe. By delving into both the infinitesimal and the cosmic, the journey remains vital for grasping how these two cornerstones of physics can coexist and ultimately inform our understanding of reality. Quantum foam is a concept that arises from the field of quantum mechanics, specifically in the context of quantum field theory. It describes the idea that at extremely small scales, on the order of the Planck length, which is about 100 billion trillion times smaller than the diameter of a proton, spacetime is not smooth and continuous, but instead exhibits fluctuations and turbulence. This foamy structure reflects the inherent uncertainties and probabilistic nature of quantum mechanics, suggesting that spacetime is dynamic and ever-changing at these minuscule scales. At the level of quantum foam, particles and virtual particles constantly pop in and out of existence, creating a sort of chaotic environment. This turbulence can influence various physical processes, potentially impacting the behavior of forces and particles at larger scales. The concept signifies that the traditional view of spacetime as a stable and unchanging backdrop is fundamentally flawed at the quantum level. The relationship between quantum foam and the fabric of spacetime implies that the characteristics of spacetime itself may depend more on quantum phenomena than previously understood. For instance, the fluctuations in the quantum foam could lead to variations in gravitational fields, thereby influencing how gravity behaves in various situations. This relationship presents a challenge for physicists attempting to merge quantum mechanics and general relativity, as the fabric of spacetime might not act in a predictable manner at the fundamental level. The notion of quantum foam also opens intriguing avenues for research into unifying theories of physics. Understanding how this foamy structure interacts with the concepts of gravity and energy might lead to breakthroughs in theories like string theory or loop quantum gravity, which aim to bridge the gap between the quantum world and the cosmological scale of reality. Exploring quantum foam could enhance our grasp of the universe's very foundation, providing insights into the interplay between quantum mechanics, gravity, and the overall nature of spacetime. Quantum tunneling is a remarkable phenomenon in quantum mechanics that allows particles to pass through energy barriers that they would not have enough energy to overcome according to classical physics. This effect becomes particularly relevant in the context of stellar processes, especially in the nuclear fusion reactions that power stars. In the cores of stars, temperatures reach millions of degrees, and nuclear fusion occurs as hydrogen nuclei combine to form helium. However, the electrostatic force between positively charged protons creates a significant energy barrier that must be overcome for fusion to happen. Classically, one might expect that only protons with sufficient energy, those moving quickly enough, would be able to overcome this barrier. Yet due to quantum tunneling, Even protons with lower energies have a finite probability of tunneling through this barrier, allowing them to fuse. This quantum effect is essential because it explains how stars can fuse hydrogen into helium even at temperatures that, without tunneling, would be too low for such reactions to occur efficiently. In fact, quantum tunneling plays a critical role in the fusion processes in stars like our Sun, significantly influencing their luminosity and lifespan. Without tunneling, the rates of fusion reactions would be drastically reduced, and stars would not be able to sustain the energy output necessary for their stability and longevity. Additionally, quantum tunneling is also significant in other stellar phenomena, such as the creation of heavy elements in supernovae. In these massive explosions, the conditions again involve nuclear reactions where tunneling can allow for the synthesis of elements beyond helium, contributing to the chemical diversity we see in the universe. This phenomenon underscores the intricate ways in which quantum mechanics operates at cosmic scales. It highlights the importance of quantum processes in shaping stellar life cycles and ultimately the chemistry of the universe itself. Understanding quantum tunneling not only illuminates stellar processes, but also emphasizes the deep connection between the subatomic world and the grand structures of the cosmos. The Great Attractor is a gravitational anomaly located in intergalactic space, specifically within a region of the universe known as the Laniakea supercluster. This region is thought to exert a significant gravitational influence on the motion of galaxies over a substantial scale, particularly in our own vicinity, which includes the Milky Way galaxy. Investigations into the motion of galaxies revealed that they are not only moving independently, but are also being pulled towards this mysterious region. The Great Attractor is estimated to be a massive concentration of galaxies, dark matter, and possibly unknown forms of matter, with the combined mass equivalent to millions of billions of solar masses. Despite its size, its exact nature remains elusive due to its location behind the dense plane of the Milky Way. This obscuration complicates our observational efforts to fully understand what the Great Attractor consists of. The influence of the Great Attractor can be observed in the peculiar velocities of galaxies, where galaxies move in ways that cannot be entirely explained by the expansion of the universe alone. Instead, their motion is affected by the gravitational pull of the Great Attractor, which is essentially drawing them towards this central point. Astronomers have noted that the Milky Way, along with its neighboring galaxies, is moving at a significant velocity towards this region, specifically towards a point in the constellation Hydra. In addition to its gravitational impact, the study of the Great Attractor has implications for our understanding of the larger-scale structure of the universe. It suggests that clusters and superclusters of galaxies are not randomly distributed, but are shaped by the underlying gravitational influences of massive structures like the Great Attractor. As researchers continue to gather more data and improve observational techniques, the Great Attractor remains a significant focal point in the quest to understand the distribution of mass in the universe and the dynamics of galactic motion within the cosmic web. Fast radio bursts, commonly referred to as FRBs, are intense bursts of radio waves that last only a few milliseconds, yet they release enormous amounts of energy, potentially equivalent to that of the Sun over many days. First discovered in 2007, these mysterious signals originate from distant galaxies, and their transient nature makes them challenging to study. Some FRBs are one-off events, while others have been observed repeating over time, prompting scientists to investigate their origins and causes. The exact mechanisms responsible for FRBs remain uncertain, but several theories have been proposed. One leading hypothesis suggests that they could be generated by highly magnetized neutron stars known as magnetars. These celestial objects are remnants of supernova explosions and possess extremely strong magnetic fields that can potentially produce intense bursts of radiation when magnetic energy is released. If magnetars experience star quakes, similar to earthquakes but on a stellar scale, it could lead to the sudden release of energy, resulting in FRBs. Another possibility involves more exotic phenomena, such as the merging of compact objects like neutron stars or black holes, where the intense gravitational forces and high-energy physics might create rapid bursts of radio waves. This scenario aligns with observations of some repeating FRBs, indicating a relation to powerful astrophysical events. Yet another intriguing theory posits that FRBs might be related to extraterrestrial technology or signals, though this idea remains speculative. The pursuit to uncover the origins of FRBs continues as researchers utilize advanced radio telescopes to track and analyze these bursts. By studying the properties of FRBs, including their dispersion and polarization, scientists hope to glean more insights into the cosmic environment of their origins and the underlying physics at play. Ultimately, understanding fast radio bursts not only raises fundamental questions about their nature, but also opens new avenues for exploring our universe, including the behaviors of neutron stars and the potential existence of phenomena beyond currently known physics. As investigations progress, FRBs have become a captivating aspect of contemporary astrophysics, revealing the complexities of cosmic events that challenge our understanding of the universe. Ultra-diffuse galaxies, often referred to as UDGs, are a fascinating class of galaxies characterized by their extremely low surface brightness and large physical size relative to their mass. They can be up to 10 times bigger than the Milky Way, while containing only a fraction of its total mass. These galaxies appear almost transparent and are often difficult to detect due to their faintness. As a result, they challenge our traditional understanding of galaxy formation and structure. The nature of ultra-diffuse galaxies suggests that they may have formed through different processes compared to more typical galaxies. One theory posits that UDGs could be remnants of ancient galaxies that have lost their gas and star-forming material due to interactions with larger galaxies or the effects of their environment. This stripping of material can occur in dense regions, such as galaxy clusters, where gravitational interactions can lead to the removal of gas that would otherwise contribute to star formation, resulting in a galaxy that expands outward but lacks the luminous stars. Another proposed formation mechanism involves the aggregation of dark matter. Given that UDGs have unexpectedly high amounts of dark matter relative to their visible mass, they may be composed primarily of this elusive material. The presence of dark matter could play a critical role in their formation by facilitating the gravitational collapse of gas clouds, leading to the creation of galaxies without the typical energetic star formation processes that characterize more standard galaxies. Observations indicate that UDGs may reside in a variety of cosmic environments, including isolated regions and dense clusters. Their distribution hints at a complex relationship between dark matter, ordinary matter, and the historical conditions of the universe. Studying ultra-diffuse galaxies helps astronomers explore fundamental questions about cosmology, such as the nature of dark matter, the processes of galaxy evolution, and the variety of outcomes in galaxy formation. As researchers continue to refine observational techniques and collect data on UDGs, these enigmatic galaxies offer an opportunity to gain deeper insights into the diversity of galactic structures and the mechanisms driving their evolution, thereby shedding light on the broader narrative of cosmic history. The Fermi paradox arises from the apparent contradiction between the high probability of extraterrestrial civilizations existing in the universe and the lack of evidence for or contact with such civilizations. Enrico Fermi, the physicist after whom the paradox is named, famously questioned, "Where is everybody?" given the vast number of stars and potentially habitable planets in the galaxy. If intelligent life is common, we might expect to see signs of their existence, yet our observations yield no conclusive evidence of extraterrestrial beings. Several proposed solutions to the Fermi paradox seek to explain this discrepancy. One possibility is that intelligent civilizations are rare, and the conditions necessary for life, particularly complex life, are exceptionally uncommon. The rare Earth hypothesis suggests that many events and conditions, such as the presence of a large moon, a stable climate, and specific geological processes, contribute to the development of advanced life, making Earth-like planets a rarity in the universe. Another possibility posits that advanced civilizations may have a limited lifespan in terms of technological capability or socio-political stability. Civilizations could self-destruct through warfare, environmental degradation, or technological mishaps before they have the chance to communicate with others or explore space extensively. This notion introduces the idea of a great filter, a significant barrier that severely limits the emergence of intelligent life. If this filter lies in our past, it may indicate that we are extraordinarily fortunate to exist. Conversely, if it lies ahead, it may suggest a grim future for humanity. Alternatively, it is argued that we simply have not been looking or listening long enough or in the right ways. The vastness of space and the limitations of our technology could mean that evidence of extraterrestrial life exists but has eluded our detection thus far. Some suggest that advanced civilizations might be deliberately avoiding contact or are using communication methods beyond our current comprehension or technology. Lastly, there are speculative theories about the nature of extraterrestrial life itself, proposing that it might not resemble our own or adhere to our understanding of what life is. Civilizations could exist in forms that are more distant or incomprehensible to us, making their presence difficult to identify or interpret. By exploring these potential solutions, we deepen our understanding of both our place in the universe and the complex dynamics that might govern the emergence and survival of intelligent civilizations. The Fermi paradox remains a compelling subject of debate in the search for extraterrestrial life and the implications for humanity's future in the cosmos. The cosmic microwave background radiation, often referred to as the CMB, serves as a vital relic from the early universe, offering a glimpse into its infancy approximately 380,000 years after the Big Bang. While the CMB is predominantly uniform in its temperature, there exists an intriguing anomaly known as the CMB cold spot. This cold spot stands out because it is remarkably cooler than its surrounding areas, specifically less than 1 part in 100,000 of the average temperature of the background radiation. Various hypotheses have been put forth to explain this peculiar phenomenon. One prominent theory suggests that this cold region could be a result of a vast cosmic void, an area where fewer galaxies exist than one would typically expect. Voids can influence the distribution of matter and energy in the universe and may lead to cooling effects, thereby creating regions that register lower temperatures in the CMB. Another interesting possibility involves the concept of large-scale cosmic structures interacting with the CMB. Some scientists propose that this cold spot might be an imprint of gravitational waves originating from cosmic inflation, the rapid expansion of the universe just after the Big Bang. These gravitational waves could have left their mark on the CMB as it traveled across spacetime, resulting in fluctuations that manifest as temperature anomalies. While these theories are captivating, the exact cause of the CMB cold spot remains a subject of ongoing research and debate. Scientists continue to analyze the data from observations while developing new models to understand better the underlying physics at play. The cold spot not only enhances our comprehension of the universe's structure, but also challenges our understanding of cosmic evolution itself. The fate of the universe is a question that has fascinated scientists and philosophers alike for centuries. As we delve into cosmology, various scenarios emerge regarding the long-term destiny of everything we know. One of the leading theories is the Big Freeze, also known as the heat death of the universe. This scenario posits that as the universe continues to expand, galaxies will drift further apart, stars will exhaust their nuclear fuel, and the universe will gradually grow colder and darker. Eventually, galaxies will dim, stars will extinguish, and only faint remnants of matter will remain, leading to a state where no thermodynamic processes occur. Alternatively, there is the concept of a big crunch. In this scenario, the universe's expansion might ultimately reverse due to gravitational attraction. If the density of matter in the universe is sufficient, it could lead to a deceleration of expansion, followed by a collapse back into a singularity, much like the state from which it originated. This would lead to all matter and energy converging, resulting in an extraordinarily hot, dense state, potentially foreshadowing a cycle akin to a cosmic rebirth. Another captivating possibility is the Big Rip, which suggests that the expansion of the universe could accelerate to the point where it eventually tears apart galaxies, stars, planets, and even atoms. This scenario hinges on the nature of dark energy, which is currently driving the accelerated expansion of the universe. Should dark energy's influence grow stronger over time, it could create a situation where all cosmic structures are annihilated in a dramatic fashion. While the ultimate fate of the universe remains open to interpretation, scientists continue to explore these scenarios through advanced observations and theoretical models. Each potential ending encapsulates our current understanding of physics, allowing us to ponder profound questions about existence, time, and the nature of reality itself. These theories inspire continued investigation and foster a deeper appreciation for the universe's complexity. Heat death, often referred to as the Big Freeze, describes a state in the universe's distant future when it has reached maximum entropy, resulting in a uniform temperature throughout. As the universe continues to expand, the energy available to do work will eventually dissipate. Stars will burn out one by one, leading to a cosmos increasingly devoid of heat and light. In this scenario, all thermodynamic processes would cease, creating a state of total equilibrium where no gradients in energy exist. This concept is rooted in the second law of thermodynamics, which states that in an isolated system, entropy tends to increase over time. As energy transformations occur across the universe, some energy becomes less available for work, dispersing into more disordered forms. Over unimaginable timescales, this process leads to stars fading and galaxies moving further apart, resulting in an increasingly homogeneous expanse. Unlike the vibrant cosmos we observe today, the universe would look stark and desolate. As stars exhaust their nuclear fuel and cease to shine, what remains will take on a cool, dim characteristic. This era, known as the degenerate era, will feature the remnants of stars, such as white dwarfs, neutron stars, and black holes, gradually cooling and vanishing. Eventually, black holes themselves might evaporate through a process called Hawking radiation, leaving behind only a diffuse scattering of elementary particles across an ever-expanding, frigid universe. In understanding heat death, we confront profound philosophical questions about time, existence, and permanence. This vision of the future serves as a reminder of the universe's dynamic nature and the ultimate fate awaiting it. While this outcome is far removed from our present experience, the concept invites contemplation about the universe's life cycle and the impermanence of all things. The Big Rip is a fascinating cosmological hypothesis that posits a dramatic end to the universe, characterized by an accelerating expansion that ultimately tears apart all matter. In this scenario, dark energy, the mysterious force driving the universe's accelerated growth, plays a crucial role. Unlike other expansion models, which may slow down or stabilize, the Big Rip envisions a future where dark energy becomes increasingly potent, leading to accelerated expansion that intensifies over time. As dark energy's influence grows, the force exerted on cosmic structures counteracts the gravitational pulls that maintain them. Initially, galaxies would be torn apart, the gravitational bonds between them becoming ineffective against the relentless push of dark energy. Subsequently, star systems would experience the same fate, with the bonds holding celestial bodies together unable to withstand the dilating forces. This process would continue, with planets, then atomic structures, ultimately being ripped apart at a subatomic level. The pivotal factor behind the Big Rip is related to the equation of state of dark energy, which describes its behavior as the universe evolves. If dark energy's density increases over time, rather than remaining constant, its effects would compound, leading to catastrophic expansion rates. Scientists are currently investigating the nature of dark energy and its long-term behavior in hopes of elucidating whether this scenario could indeed be a plausible outcome for our universe. Imagining such a violent end prompts reflection on the fundamental nature of existence and the forces shaping our cosmos. The Big Rip serves as a reminder of the inherent unpredictability of the universe's fate, challenging our understanding of time, space, and the limits of reality itself. While this scenario remains speculative, it underscores the complexities and mysteries that continue to fuel scientific inquiry and popular imagination alike. The Big Crunch presents a striking contrast to the current expansion of the universe, which has been accelerating since the discovery of dark energy. Currently, galaxies are moving away from one another, and the overall trajectory of the universe suggests that it is growing larger over time. The cosmic microwave background radiation and observations of distant galaxies have led scientists to a consensus that the universe is not just expanding, but doing so at an accelerating pace due to this enigmatic dark energy. In a Big Crunch scenario, however, this expansion would eventually halt and reverse direction under the influence of gravity. If the density of the universe is high enough, the gravitational attraction of all the mass within it could overcome the prevailing forces driving expansion. Rather than galaxies drifting apart, matter would begin to coalesce, resulting in a dramatic reversal where everything would draw closer together, culminating in a cataclysmic collapse. As this contraction progresses, cosmic structures would fall into one another. Galaxies, stars, and even planets would merge in the dance of gravitational forces, leading to an increasingly dense and hot environment. Ultimately, all matter and energy would converge back into a singularity, reminiscent of the initial conditions of the Big Bang. This transformation represents a complete pivot from the expansive, cooling universe we know today. The Big Crunch not only highlights the conflict between potential gravitational attraction and dark energy's effects, but also offers a cosmic perspective on cyclical models of existence. If such a scenario were to unfold, it would transform our understanding of time and the universe, suggesting that it might undergo repeated cycles of birth and rebirth. This vision challenges the notion of linear progression in cosmic history and prompts deep reflections on the nature of existence itself. Dark energy plays a pivotal role in influencing the ultimate fate of the universe, acting as the driving force behind its accelerated expansion. Discovered through observations of distant supernovae, dark energy is characterized as an unknown repulsive force that permeates space. Comprising approximately 70% of the universe, its effects affect not only the expansion rate, but also the long-term dynamics of cosmic structures. As the universe expands, the gravitational forces from galaxies and clusters of matter would typically decelerate that expansion. However, dark energy operates contrary to this expectation. Instead of slowing down, the universe's expansion has been found to accelerate, leading to a curious phenomenon where galaxies are moving away from us at an increasing rate. This suggests that dark energy exerts an influence that outweighs the attractive forces of gravity on large scales. The behavior of dark energy is central to various theoretical outcomes for the universe. If dark energy remains constant over time, the universe might approach a state of heat death or big freeze, culminating in a cold, dark existence devoid of significant cosmic activity. Alternatively, should dark energy's effects intensify, a possibility considered in scenarios like the Big Rip, the universe could be torn apart as expansion accelerates unchecked, affecting everything from galaxies to subatomic particles. Understanding dark energy, therefore, becomes crucial for predicting the universe's long-term destiny. Scientists continue to investigate its properties, seeking to unravel the mysteries surrounding this puzzling component of the cosmos. The insights gained may not only shape our comprehension of the universe's fate, but also provoke profound reflections on the fundamental forces that govern existence itself. Space telescopes like the James Webb Space Telescope significantly expand our view of the universe by providing unprecedented capabilities to observe the cosmos across various wavelengths, particularly in the infrared spectrum. Unlike ground-based telescopes, which are limited by the Earth's atmosphere, the James Webb is positioned beyond this veil, allowing it to capture clearer and more detailed images of celestial objects. This advantage facilitates the exploration of phenomena that are often obscured, such as dust clouds surrounding star-forming regions or the faint light emitted by distant objects. Infrared observations are particularly critical for studying cool or distant celestial bodies. For instance, many galaxies and stars are shrouded in dust, which blocks visible light. The James Webb's ability to observe infrared radiation enables scientists to penetrate these clouds, unveiling details about star formation and the composition of distant galaxies. This capability allows researchers to gather insights into the processes that have shaped the universe over billions of years. Furthermore, the telescope's design includes advanced instrumentation that significantly enhances its sensitivity and resolution. By observing farther back in time, up to more than 13 billion years, Webb can capture images of the universe as it appeared shortly after the Big Bang. This deep field exploration contributes to our understanding of galaxy formation and evolution, shedding light on periods in cosmic history that were previously inaccessible. The discoveries made possible by the James Webb Space Telescope are set to transform our comprehension of the universe. As it gathers and analyzes data from various cosmic phenomena, it will answer fundamental questions about the formation of stars and galaxies, the nature of dark matter and dark energy, and the possibility of habitable worlds beyond our solar system. The insights gained from this remarkable observatory promise to paint a richer, more nuanced picture of our universe and our place within it. Gravitational lenses are fascinating cosmic phenomena that occur when a massive object, such as a galaxy or galaxy cluster, lies between a distant light source and an observer on Earth. The gravitational field of this foreground object bends the path of light coming from the background source due to the distortion of spacetime, a prediction of Einstein's general theory of relativity. As a result, this can create multiple images, arcs, or even rings of the distant object, enhancing the visibility of celestial bodies that would otherwise be too faint to observe. Astronomers utilize gravitational lenses as powerful tools for studying the universe. One of the primary applications is in the investigation of distant galaxies. By analyzing the light that has been bent and magnified, astronomers can glean insights into the properties of these remote galaxies, including their composition, structure, and star formation rates. Gravitational lensing can often amplify the brightness of the background objects by several times, making it possible to observe galaxies that are billions of light years away, effectively pushing the boundaries of what we can explore. Additionally, gravitational lenses can provide valuable information about the foreground lensing mass. By studying the distortions caused by the gravitational lens, astronomers can derive estimates of the mass distribution of the lensing object. This means they can gain insights into dark matter, since much of the mass of these lenses often remains invisible. Analyzing how the light is bent helps scientists understand the distribution not only of visible matter in the universe, but also of the elusive dark matter that dominates the mass content of galaxies and clusters. Gravitational lenses serve as cosmic magnifying glasses, allowing astronomers to delve deeper into the structure and evolution of the universe. As they continue to study these phenomena, scientists gain critical data that enrich our understanding of cosmic formation, the distribution of matter, and the fundamental workings of gravity itself. This opens up new avenues for exploration and discovery, significantly enhancing our view of the cosmos. Neutrino detectors play a critical role in our exploration and understanding of cosmic phenomena by capturing elusive neutrinos, which are nearly massless particles produced in vast quantities during various high-energy processes in the universe. Neutrinos are generated in events such as supernova explosions, interactions in the Sun, and the collisions of cosmic rays with matter. Due to their weak interactions with other particles, neutrinos can travel immense distances through space without being absorbed or deflected, providing a unique means to observe the most energetic and distant events in the cosmos. One of the most significant contributions of neutrino detectors is their ability to probe the inner workings of supernovae. When a massive star explodes, it releases an immense burst of energy and produces an unprecedented number of neutrinos in a fraction of a second. Detecting these neutrinos allows scientists to study the dynamics of the explosion, providing insights into the processes that lead to the formation of neutron stars or black holes. This timely data is crucial for understanding stellar evolution and the life cycles of galaxies. Moreover, neutrino detectors also facilitate the investigation of high-energy cosmic rays, which are among the most energetic particles in the universe. When cosmic rays collide with atomic nuclei in the atmosphere, they can produce neutrinos. By monitoring the interactions of these neutrinos in deep underground detectors, scientists can trace the origins of cosmic rays, identifying their potential sources, which may include active galactic nuclei, gamma-ray bursts, or other extreme astrophysical environments. In tandem with telescopes and other observatories, neutrino detectors enhance our multi-messenger understanding of the universe, combining data from light, gravitational waves, and particles. Recent advances in neutrino detection technology continue to improve sensitivity and the ability to pinpoint the sources of these high-energy neutrinos more accurately. As researchers explore the uncharted territory of neutrino astronomy, the insights gained promise to unlock further mysteries surrounding the most violent and energetic processes that shape our universe. Interferometry is a powerful technique used in astronomy that enhances the resolution and sensitivity of observations by combining the light received from multiple telescopes. This method takes advantage of the wave nature of light, allowing astronomers to capture and analyze subtle differences in the light waves collected from distant celestial objects. By observing the same astronomical source with two or more telescopes situated at various distances apart, interferometry can create a more detailed image than a single telescope could achieve alone, effectively functioning as a much larger virtual telescope. The principle behind interferometry relies on a phenomenon called interference, which occurs when two or more light waves superimpose upon each other. When the captured light waves from different telescopes combine, they can either amplify each other, leading to constructive interference, or diminish one another, resulting in destructive interference. By precisely measuring these interference patterns, astronomers can extract information that reveals details about the brightness, shape, and distance of the observed object. There are various types of interferometry used in astronomical observations, including radio interferometry and optical interferometry. Radio interferometry, for example, is employed with arrays of radio telescopes like the Very Large Array. This setup can achieve resolutions significantly sharper than what a single radio telescope could provide, enabling scientists to study celestial phenomena in immense detail, such as the structure of distant galaxies, the dynamics of stars, and the nature of cosmic masers. Optical interferometry, on the other hand, focuses on combining light from optical telescopes, improving the resolution of observations in visible light. Projects like the Very Large Telescope Interferometer in Chile demonstrate how this technique can allow scientists to investigate features around stars, measure their diameters, and even detect exoplanets. By integrating the capabilities of multiple telescopes, interferometry transforms our ability to observe and understand the universe. It unlocks a treasure trove of information about the intricate structures of celestial objects, their distances, and their physical characteristics, leading to advancements in our knowledge of cosmology, stellar evolution, and the dynamics of galaxies. Future space-based observatories hold the potential to revolutionize our understanding of the cosmos by providing unprecedented access to a wealth of data about the universe across various wavelengths. These advanced observatories will be positioned beyond the Earth's atmosphere, allowing them to avoid light pollution and atmospheric interference that can hinder observations. This capability will enable scientists to explore the universe in more detail and with greater clarity than ever before. One of the key advantages of these observatories is their ability to observe in a wider range of wavelengths, including ultraviolet, infrared, and even X-rays. For instance, the James Webb Space Telescope focuses primarily on infrared light, allowing researchers to study the formation of stars and galaxies much earlier in the universe's history. Future observatories, like the proposed NASA mission named the Habitable Worlds Observatory, aim to directly analyze the atmospheres of exoplanets, searching for signs of habitability or even biosignatures, which could transform our understanding of life's potential in the universe. Additionally, future space-based observatories may enhance our capability to investigate dark matter and dark energy, which together constitute about 95% of the universe's total mass and energy content. By utilizing advanced imaging techniques and large-scale surveys of galaxies, these observatories could provide insights into the distribution and properties of dark matter, informing theories about the universe's structure and evolution. Understanding dark energy's role in cosmic expansion remains one of the most significant challenges in cosmology, and next-generation observatories will provide vital data to help address these questions. Furthermore, developments in technology will allow for improved instrumentation and innovative observational strategies. These advancements will lead to enhanced sensitivity, enabling the detection of fainter celestial objects and more precise measurements of cosmic phenomena. The cumulative data generated from these space missions will help create a more comprehensive picture of the universe's history, whether it's mapping the cosmic microwave background radiation or investigating the formation of the first stars and galaxies. Future space-based observatories promise to expand our horizons, allowing us to probe deeper into the mysteries of the universe. They will help us refine existing theories, develop new models, and enhance our overall understanding of the cosmos, offering insights that challenge our perceptions and reshape our place within the universe. Modified gravity refers to alternative theories that propose changes to our understanding of gravitational interactions, particularly in the context of explaining cosmic phenomena without relying on dark matter. Traditional physics, as described by Newton's law of universal gravitation and Einstein's general relativity, has served as the foundation for our understanding of gravity. However, observations of galaxies and galaxy clusters have consistently suggested discrepancies between the observed behavior of these celestial bodies and the predictions made by these gravitational theories. In galaxies, for instance, stars orbit the center at unexpectedly high speeds. According to Newtonian physics, we would expect the outer stars to move more slowly due to the diminishing influence of gravity from the visible matter. Yet they maintain high velocities, leading to the conclusion that there must be unseen mass, dark matter, providing the necessary gravitational pull. Modified gravity theories, such as modified Newtonian dynamics and others, attempt to explain these observations without invoking dark matter by suggesting that gravity behaves differently at low accelerations, which often occur in the outskirts of galaxies. These modified theories challenge our understanding of dark matter by proposing that the effects ascribed to this mysterious substance could instead be accounted for through adjustments to gravity itself. This approach not only offers alternative explanations for the dynamics of galaxies, but also raises questions about the nature of spacetime and gravity on larger cosmological scales. If gravity is modified, it could influence cosmic structures in ways that would alter the conventional modeling of the universe, including the formation and evolution of galaxies. However, while modified gravity theories show promise, they face challenges in explaining certain observations that dark matter can more seamlessly account for, such as the cosmic microwave background fluctuations and the large-scale structure of the universe. This ongoing debate reflects a frontier in astrophysics as researchers strive to resolve discrepancies and deepen our understanding of fundamental forces. As observational technologies advance, astronomers continue to gather data that could help determine whether dark matter, modified gravity, or a combination of both plays a role in the cosmos. This exploration not only investigates the nature of gravity, but also pushes the boundaries of our comprehension of the universe, inviting new questions and theories about the underlying laws that govern its behavior. Loop quantum gravity is a theoretical framework that seeks to reconcile the principles of quantum mechanics with Einstein's general relativity, addressing one of the most significant challenges in modern physics. While general relativity describes gravitational interactions on a macroscopic scale, illustrating how massive objects warp spacetime, quantum mechanics governs the behavior of fundamental particles and forces at the subatomic level. These two pillars of physics work well in their respective domains, but yield conflicting predictions when conditions involve extreme gravitational forces, such as those present in black holes or the very early universe. At the heart of loop quantum gravity lies the idea that space-time is not a continuous fabric, but rather is composed of discrete, quantized units reminiscent of atomic structures. This concept posits that space-time can be divided into tiny, loop-like structures called spin networks. These networks represent the quantum states of the gravitational field, allowing space-time itself to emerge from the underlying quantum mechanical properties. In this view, geometry becomes granular, akin to pixels in an image, with the fabric of reality being woven together by these fundamental loops. One of the key contributions of loop quantum gravity is its approach to resolving singularities, which occur in traditional general relativity scenarios, such as black holes or the Big Bang. By incorporating quantum principles, loop quantum gravity predicts that physical quantities such as area and volume are quantized. This implies that rather than collapsing into an infinitely dense point, the structure of spacetime behaves differently at extremely small scales, potentially avoiding the singularities that plague classical theories. Moreover, loop quantum gravity emphasizes a background-independent formulation, meaning that its structure does not presuppose a fixed spacetime backdrop, unlike many other quantum gravity treatments. This aspect aligns more closely with general relativity's dynamic understanding of gravity and spacetime, proposing a more integrated model for the universe's behavior. As researchers continue to develop and test the implications of loop quantum gravity through mathematical and computational approaches, this framework holds the promise of shedding light on the unification of quantum mechanics and general relativity. Although still in its infancy, the insights gained from this effort could revolutionize our understanding of the universe, providing a more comprehensive picture of the fundamental laws that govern both the cosmos and the microscopic realm. The holographic principle is a provocative concept in theoretical physics that suggests our three-dimensional universe may be encoded on a two-dimensional surface, much like a hologram. This idea emerged from considerations in black hole thermodynamics and string theory, positing that all the information contained within a volume of space can be represented on its boundary. The principle proposes that the fundamental nature of reality may be fundamentally lower dimensional, hinting at a deep connection between information, geometry, and gravity. The origin of the holographic principle can be traced back to studies of black holes, particularly the work of physicists like Jacob Bekenstein and Stephen Hawking. They discovered that the entropy of a black hole, the measure of its disorder, proportional to the area of its event horizon rather than its volume. This finding implied that information related to the contents of a black hole doesn't exist within the ball of space itself, but rather on its boundary, leading to the suggestion that our entire universe might share a similar characteristic. If the holographic principle applies on a cosmic scale, it has profound implications for our understanding of space, time, and gravity. For example, it challenges the notion of locality, the idea that objects are only directly influenced by their immediate surroundings, by suggesting that at a fundamental level, all points in space could be interconnected through the information encoded on surfaces. This perspective may also provide insights into the behavior of spacetime near quantum gravitational boundaries and help address questions about the reconciliation of gravity with quantum mechanics. Furthermore, the holographic principle could help illuminate the nature of dark energy and dark matter, which together comprise much of the universe's content, yet remain elusive to direct observation. By understanding how information encoding operates in a holographic universe, scientists may develop new theoretical frameworks that unify disparate aspects of physics or provide explanations for currently enigmatic phenomena. As researchers continue to explore the ramifications of the holographic principle, it remains a vibrant and dynamic area of inquiry. While still theoretical, its implications challenge our intuitions about reality, pushing the boundaries of our understanding of the universe and suggesting that the true nature of existence could be far more intricate than our classical perceptions allow. String theory proposes a radical shift in our understanding of the fundamental nature of the universe by positing that the basic building blocks of reality are not point-like particles, but rather one-dimensional strings, which can vibrate at different frequencies. This concept arises from the need to unify the four fundamental forces of nature: gravitational, electromagnetic, weak nuclear, and strong nuclear, within a single theoretical framework. String theory seeks to provide a consistent description of how these forces interact at the most fundamental level, particularly in the realm of quantum gravity. In string theory, the properties of particles such as mass and charge emerge from the vibrational patterns and modes of these fundamental strings. Just as different vibrations of a guitar string yield different musical notes, various modes of vibration in string theory result in different particles. This insight allows string theory to potentially unify all known particles and forces into a cohesive framework, offering a compelling candidate for a theory of everything. Another intriguing aspect of string theory is its requirement for additional spatial dimensions beyond the familiar 3 of space and 1 of time. In its simplest forms, such as 10 or 11 dimensions, the extra dimensions can be compactified or curled up in ways that remain hidden at everyday scales. These additional dimensions are essential for the mathematical consistency of string theory and allow for diverse physical phenomena, including the various interactions of particles. String theory also introduces the concept of supersymmetry, which postulates that for every known particle, there exists a corresponding partner particle with different spin properties. Although supersymmetry has yet to be confirmed through direct experimental evidence, it could provide solutions to several outstanding questions in physics, such as the hierarchy problem and the nature of dark matter. As string theory continues to evolve, researchers are exploring its implications for various aspects of cosmology, particle physics, and quantum gravity. While it remains a developing field with many theoretical challenges, the ideas posited by string theory promise profound insights into the very fabric of the universe, inviting a re-evaluation of our understanding of space, time, and the fundamental interactions that govern reality. Cosmic inflation is a theory proposed to explain a crucial phase in the very early universe, characterized by an extremely rapid expansion that occurred within a fraction of a second after the Big Bang. This phenomenon suggests that the universe underwent exponential growth, expanding at a staggering rate, much faster than the speed of light, over a short timescale. Inflationary theory was introduced in the early 1980s by physicist Alan Guth and others to address several puzzling observations regarding the large-scale structure of the universe. One of the key implications of cosmic inflation is its ability to explain the observed uniformity of the universe, known as isotropy. On large scales, the universe appears remarkably homogeneous, with galaxies and structures distributed uniformly in all directions. However, if we look back to the time of the Big Bang, there were regions that were causally disconnected, meaning they could not have communicated or interacted with each other due to the finite speed of light. Inflation addresses this issue by proposing that these regions were once very close together and uniformly hot before being rapidly stretched apart, resulting in a smooth and even distribution of matter and energy across the universe. Moreover, inflation predicts that tiny quantum fluctuations that occurred during this brief period of rapid growth were stretched to cosmic scales. These fluctuations served as the seeds for the large-scale structure we observe today, such as galaxies and galaxy clusters. As the universe continued to expand, these initial variations evolved under the influence of gravity, eventually leading to the formation of the complex structures we see throughout the cosmos. Cosmic inflation also provides explanations for other observations, such as the uniformity of the cosmic microwave background radiation. This relic radiation, a remnant of the early universe, is nearly isotropic, but features slight temperature fluctuations. Inflation helps account for the relative uniformity of this radiation while also allowing for the tiny deviations necessary for the eventual formation of galaxies. As research continues, cosmic inflation remains a compelling area of study, with ongoing efforts to test its predictions and explore its implications for the early universe. By offering a cohesive framework for understanding several key properties of the universe, inflation enhances our comprehension of cosmic evolution and deepens our insights into the fundamental laws that govern existence.